Hey, hi everyone. Welcome back to my YouTube channel. My name is Savita, and I'm back with another exciting and important video. So, guys, in this particular video, we're going to discuss the remaining part of the LLM quantization. Yes, guys. So, in the first part, we discuss all the fundamental concept of the LLM quantization. Now, in this video, we'll see the advanced concept of the quantization. So I started with this playlist, guys. So far I recorded 12 video inside this fine tuning playlist, and this LLM quantization is also part of this playlist. Okay. So if you haven't seen so far, please go and check with my YouTube channel. So inside the playlist section, guys, you will find out this LLM fine tuning playlist. Now, apart from this one, you will find out the other playlists also, like LangChain, LangGraph, Advanced RAG, Multimodal RAG, okay, then Basic RAG, and then here inside this playlist Generative AI from basic to advanced, you will find out all the video in a sequence, right? So so guys, first of all, let me show you the syllabus, that what all thing I discussed in the previous video inside this part one, and then I'll come to the LLM quantization, okay, the introduction of it. So here is all the notes which I prepared for all of you guys. So I discussed till here the type of the quantization, okay, and this notes and all everything I provided over my GitHub. You can check out that link in the description. Now, guys, in today's video, we'll discuss the LLM advanced quantization introduction. Then we'll come to the GPTQ. Okay. Then after the GPTQ, we'll discuss about the AWQ, which is called Activation Aware Weight Quantization. Then QAT, Quantize Aware Training, and LLM, how we can do it. We'll discuss it. Then the last one is the GGUF and the GGML. So how we can convert our file, our binary file into the GGUF, and what was the GGML, right? So every sort of a thing we're going to discuss over here now. So let me give you the quick recap that what all thing we have discussed in the first part. So this is the entire syllabus of this quantization course, guys. So in the first part, I discussed like what is a quantization, why do we quantize, then differences between RAM and VRAM. Then we discuss the data type and the memory consumption. Okay, we discuss about the precision in the deep learning, the formula of the quantization and the dequantization. Then we understood about the symmetric quantization, asymmetric quantization. We understood about the tensor quantization and per channel quantization. I haven't went through with this concept in a very detailed way, but don't worry, guys. In today's video, we'll talk about along with the example. In the previous video, I just given you the overview. Then, guys, we talked about this type of the quantization like PTQ, QAT. PTQ means what? Post-training quantization, and QAT means what? Quantize aware training. Then this next thing, static PTQ and the dynamic PTQ. So it was a part of the PTQ only. Then we understood some other concept of the quantization, like what was a calibration data, what is a quantize error. Okay, and then guys, we have performed one practical. So I shown you all this quantization technique, PTQ, QAT, static PTQ, dynamic PTQ using the neural network, right? So your fundamental could be strong over here. All right. Now, guys, we have to discuss some advanced concepts. So we'll start from the LLM quantization introduction. Then we'll come to the GPTQ, which is also called the gradient post-training quantization. Then AWQ, activation aware weight quantization. Then GGML, Georgi, Gerganov, machine learning. And then Gerganov journal unified format. Okay, this is the full form of the GGUF. Then, guys, we'll come to the practical example of the LLM. So I prepared all the practical example, as you can see. Let me show you it over the browser. So this is the first one, GPTQ. Then it's a AWQ. Now here is a GGUF and GGML. And I prepared one example for the QAT as well, right? So each and every thing is with me. Now I just have to explain you. And yeah, then, guys, your quantization part will be done. After this one, I will start the fine tuning. I will upload the fine tuning video, like how you can fine tune the any LLM model with the Hugging Face, with the basically other different framework and all, and with the different techniques which is like being used in the current industry. Okay. Now, if you will go and check with my YouTube channel, guys, so here you will find in the description, guys, you will find out a different links. Now, one link is very special, this one-to-one call. So if you want to connect with me one-to-one for clarifying your doubt or any sort of a thing, right? So I mentioned a couple of services over here. So services wise, if you want to be get generative AI interview preparation guide, if you want to connect for the quick chat, if you want to connect for the career guidance, resume review, mock interview, interview preparation. So I'm there for you. You just need to book your call, and then I will be there at a like at the book time. Okay. Now, guys, one more thing. Let me clarify over here. So here you can see my video length is quite huge. If you will check with respect to each and every video. So why I'm uploading a huge video and the long content, so that I can cover up each and everything. So you don't need to go anywhere here and there, because in 10 to 15 minutes of video, what I can explain you, right? You also understand this part. So that's why, guys, I'm uploading this longer video with all the concept, the entire concept, so that you can follow each and everything at the single place. If you're coming to my channel, so here you are not going to waste your time. At least you are getting that particular concept at least 50%, which I'm like thinking. Okay. So if you're thinking that this video is like quite long, quite huge, so what you can do, guys, you can watch it at 1.5x or 2x for the better experience, and just to save your time. Okay, this is a one and only suggestion for all of you guys. Now let's start with the concept, like uh, what is a LLM quantization. Okay, and let's see the complete introduction of it. So first, guys, let's take a recap of all the terms which we understood so far. Let me zoom my screen. Yep, now I think it is visible. So here the first term is the FP. FP means what? FP means floating point. Okay. I discussed this particular thing in a very detailed way. If you don't know about it, you can go and check with the previous video. Then integer, right? What is the integer? Int 8, int 4, how much memory it is taking, uh, right? And the range of this particular data type, the different type of the integer, each and everything I discussed in the again previous video. Then PTQ, it is called post-training quantization. So we quantize a model after the full training without retraining. So we are not going to perform any sort of a training. We are just going to be quantize our weight right after the training. Okay. And this is very popular technique in the world of the quantization. This is called PTQ and GPTQ, right? GPTQ. So GPTQ is an extension of this PTQ only, guys. Then we have QAT. QAT means what? Quantization aware training, simulate quantization during the training process. Okay. So while we are training a model, at that time only we are going to quantize the weight. So the thing we do inside the QAT technique. Okay. Then we have this GPTQ. GPTQ basically it's a advanced PTQ technique, post-training quantization technique. It is only for the LLM models. Okay. Now here I written some description of it. As you can see, originally stands for gradient post-training quantization. So guys, G means it's not a GPT. G stands for G stand for gradient. Okay, gradient post-training quantization. It is specific to PTQ technique. As I told you, it is a specific to the PTQ technique designed for transformer. So it is only designed for the transformer-based model. People confuse it with the generative pre-trained transformer quantization, or GPT or GPT post-training quantization. But this is not a correct name of it. The correct name of this particular technique is a gradient post-training quantization. Now where you will find out this actual name and all, so yeah, simply you can check out with the actual research paper. Let me show you a couple of research paper. So guys, whenever we talk about this quantization, so regarding this quantization, huge research have been done, right? So this is one of the repository where you will find out almost all the research paper regarding the quantization. So you just need to visit the readme page of this repository and see, guys, around uh, 2 to 300 research paper you will get over here with respect to the different modality and all, and with respect to the different quantization technique, right? The quantization is being performed in how many ways on how many model. So regarding each and every model, regarding each and every technique, you will get a research paper over here, right? Now guys, it's hard to find out a correct research paper or the important research paper among all these ones. So I kept some important research paper for all of you. Here is a one. So this HAWQ, Hessian aware quantization of neural network. This is one of the important paper. Now where it lies, I'll come to that. Now here one more is there, AWQ, activation aware weight quantization for LLM comparison and acceleration. So guys, this is again one of the important research paper. The complete AWQ technique, it depends on this only. Then guys, one more is there, GPTQ. So accurate post-training quantization for generative pre-trained transformer. Okay. So the name was the accurate post-training quantization for generative pre-trained transformer, right? But actually, guys, the technique is called gradient post-training quantization. If you will go and check with this research paper, you will get that. So, generative pre-trained transformer means what? I think you know, you are familiar with this specific word. This is nothing. This is our favorite GPT, right? So, first, guys, this technique was invented for the GPT itself, for the GPT model, and the technique name was what? The technique name was the post-training quantization. Okay, gradient post-training quantization. Then this research paper is very important if you want to be understand the fundamental concept of the LLM quantization. But then for sure you should check out with this research paper. Okay, then again one more research paper, quantization and the training of the neural network for efficient integrated integer arithmetic only inference. So guys, this is a little older research paper which was published in 2017 itself. But guess if you want to understand the fundamental terms and terminology with respect to the quantization, then for sure you should check out with it, right? So here left hand side you can see the submitted date. So the submitted date is on 15 December 2017. Then guys, one more very famous research paper which was published recently in the last year only. So the research paper name, the era of the 1-bit LLM. So what is the meaning of it? What is a 1-bit LLM? You know, guys, if we're talking about the int4, right? So int4 means what? 1 byte. How many memory this int4 is taking? So int4 is taking 1 byte memory, means 4-bit, right? So we are executing our weight value, this w value on we are executing our w value on the 1 byte, okay, on top of the 8 bit. If we're talking about the 1 byte, it is equal to 8 bit. If we're talking about 0.5 byte, so it is equal to the 4 bit, right? So we are able to quantize our weight up to the 0.5 byte as well. Means we are executing our weight, we are storing our weight onto 0.4, 0.5 byte, means 4 bit, right? But guys, see, just look over here what they're saying. They're saying the era of 1-bit LLM means the specific weight we can actually store at 1.58 bits. Okay, we can store at this particular level. So see, like how much reduction, how much reduction is there in terms of memory? Means if we're talking about 0.5 byte, means 4 bits, we are going to be store our 1 bit value on 4 bit. But now guys, see what kind of techniques and all have been invented. We are able to reduce the size of the memory till 1 bit. Okay, this is called the like how much? I think 0.1 byte, right? So yeah, that's kind of crazy work is going on, and this is a very good research paper, and for sure you should read it out, and definitely we can definitely guys we can do the practical of it. Okay, so complete theory practical sorry complete theory formulas and all everything you will get over here inside this research paper. So if you're not able to read it like completely, at least you should go through with their headings and the specific like some important points. Okay, now coming to our slide again. So AWQ means what? As I told you, activation aware weight quantization, focus on scaling weight with respect to activation for the better accuracy. Okay, in int 8 and int 4. So I think I already discussed about this AWQ, which is activation aware weight quantization, right? So this AWQ technique we perform, right? When we perform it, when we are training our model. Okay, at that time itself we are going to be quantize our weight as well as the activation value as well. Okay, then guys, here is two more interesting term. The next term is the GGML. Okay, and the next another term you will see, which is called GGUF. So what does it mean, guys? So GGML is called Georgi Gerganov machine learning library for the inference. So he was a scientist, he was a like very famous scientist. Okay, so he has created this particular library. The library name was the GGML itself, and this library was completely written in C language. And this library mainly have been written to do the inferencing. Means already we have created a model, we have trained a model. Now, if we want to do the inferencing of that particular model, okay, so how we can do it faster? Because if we are going to be loaded on some server, right? So because of the size, because of the Python interpreter is going to be take time, right? Python interpreter is a little slower compared to the C. So what this person have been has done? So this person actually converted the entire like code base on all everything in C itself, and he was executing over the C interpreter only, C compiler only. just for the inferencing, not in terms of the training, right? So this person has written the GGML, and now whatever framework you are seeing nowadays in a market, okay, so llama cpp, mistel and all, mistel cpp and all, right? So this framework have been written on top of this library only, the GGML library only, okay. So now you are able to think like what kind of work the person have been has done at that time, right? So it is supporting a CPU, it is supporting the GPU only. So you can think in such a way this GGML is nothing. It's just an inferencing engine. Okay, it's just an inferencing framework which have been written in C language. Here we can load our model, which is like quite faster compared to the Python one. We can load our model, okay, on top of the C compiler, C interpreter, and then we can execute it just for the inferencing, right? Now GGUF, what is a GGUF? So guys, GGUF is nothing. It's just a file format. Okay, we're talking about the GGUF. It is a file format. So earlier, guys, for the GGML, this guy Georgi Gerganov, it has written like when he has written this GGML library, na. So it has the file, model file was saving in the form of bin. Okay, GGML bin, right? The file name was a ggml.bin. Now, guys, we have one more advanced version of this GGML bin only. Okay, this is called GGUF. So we're talking about the GGUF. So it is nothing. It is a file. Okay, it's a file extension. So the full form of it, George Journal Unified Format, successor to the GGML binary format. Okay, so it is used to store the quantized model. So whatever quantized model we have, we can store in the GGUF format. I hope, guys, you understood that, understood the meaning. You understood the meaning of this each and every term, which is very much important. Now, what we have to do, guys, we have to understand the flow, right? When this PTQ was used, what's the meaning of the PTQ, where this GPTQ lies, what is the GGUF, then what is the llama CPP or this GGML. If we are able to understand the flow, right? So in that case, what will happen, we are able to understand the flow. So we'll be able to keep the right thing in the right place. Okay, our thinking would be clear in that case. Okay, if someone would say that, okay, what is the llama cpp, you will say, okay, llama cpp is nothing, it's just an inferencing engine. If someone will ask you what is the gguf, gguf is nothing, it is just a like file format. If someone will ask you, okay, tell me what is the ptq, so ptq is nothing, it is a type of the training quantization. Okay, sorry, it's a type of the quantization, right? Someone will ask you, okay, what is a GPTQ? GPTQ is nothing. It is a grading based post-training quantization for specifically for the LLM model, right? So if we are able to understand the flow, right? So when this which term is being used, so the thing will be easy for us, right? So let's take a look onto it, and let's try to understand the flow of each and everything, guys. So guys, first understand the complete flow. So as a flow, guys, I written this one line summary. So you can see we have PTQ QAT, what it is. So it is a quantization technique, means how quantization is being done. Then GPTQ AWQ, it is a quantization algorithm. Okay, so the GPTQ AWQ is, it comes under PTQ only. So it is an enhancement of the PTQ method. Then we have a GGUF, means model file format used for saving and exporting the quantized model. Then we have this GGML. So what is a GGML, guys? It is an inferencing runtime engine that runs the quantized model like GGUF model. So guys, first we have PTQ, means it is a technique, post-training quantization technique. Then we have GPTQ, it's a specific technique for quantize the LLM model. Then GGUF, after the quantization, will convert into the GGUF format, and then we'll run it over the llama CPP or over the GGML. So here is a complete theory of the like GGML, llama CPP and all. And this is the example, as you can see. So what we are doing, what we are going to do now, we are going to be understand along with the example. So let me explain this entire flow over here. Give me a moment, guys. So let's say we have a technique. Let's say we want to quantize the model. So what we do, we want to quantize the model. Now for quantizing a model, how many techniques we have? We have two techniques. The first technique is called PTQ, post-training quantization. The second technique is called QAT, quantize-aware training. Okay. Now guys, if we want to quantize the LLM model, specifically large language model, so for that, again, we have two techniques. Okay. In the PTQ itself, I am saying the first is called the GPTQ. Okay, GPTQ. This is not a technique actually, it's a algorithm. Okay, it's a PTQ algorithm. So GPTQ. Then we have one more which is called this one AWQ. Okay, AWQ. Now in GPTQ, what we are doing in GPTQ, guys, see, this is all, both are post-training quantization technique, right? So let's say either we are performing this GPTQ or we are performing this AWQ, right? So after performing the quantization, what we'll get? We'll get the file, okay, the quantized file, which is called bin file, .bin file. Now this bin file, we are converting into what? We are converting into the GGUF, okay? So we are converting into GGUF in this particular format. It is like a little more effective format, okay, GGUF. Then after converting it into where we are executing it, so we are executing it in engine, right? So in which engine? We can execute it inside the GGML engine, or we can execute it over the llama.cpp, okay, llama.cpp, okay. Or this also, let's say we are performing this AWQ technique. In the AWQ technique, what are the differences between the GPTQ and the AWQ? In the AWQ, we are quantize the activation value also. So here, along with the weights, we are going to quantize the activation value also. Quantize activation value plus weights, okay, plus weights. So this is the difference. So here in the GPTQ, we are just quantizing the weights value, okay, weights only. And here we are quantizing the activation value as well as the weight. So again, we'll get a file. So this file would be the GGUF file. Now we are going to execute it over the GGML or the advanced one, which is called the, let's say, llama.cpp, okay, llama.cpp. I hope, guys, now you understood the complete flow. Now what about this QAT? So this QAT is also one more type of technique. So we're talking about the QAT, guys. So let me talk about this QAT. So this QAT is called the Quantized Aware Training, okay, uh, Quantized Aware Training. Quantized Aware Training means what? At the time of the training only, we are going to perform the quantization. So for this quite also, we are doing it specifically for the large language model, for the LLM. So we have some algorithm, okay. And after performing this particular algorithm, what we can do effectively, we can do the QAT. Now once we'll do the QAT, then what we'll get, guys? Again, we'll get either the bin file, okay, uh, either the bin file, or what we'll get, guys? We'll get the GGUF file. Then what we can do further, we can run it over the either the GGML, or we can run it or where we can run it, over the llama.cpp. I hope this thing is clear and everyone is able to understand this entire flow, right? If not, you can again rewind it, and for sure, guys, you will be able to get it. Now coming to the next part. So now here, guys, you can see what we have. We have just a second. So we have this particular example. This example is very much important. With this particular example will give you little more understanding. So let's suppose you have a llama 3 model, okay. Now what you have to do, you have to quantize it. So you have this llama 3 model with the FP16 weights, okay. What you will do, you will perform the quantization using the GPTQ technique. This is a post-training quantization technique, okay. Got it? Then what you will do, you will export the quantized model in a GGUF format, okay, which is a compatible with the llama CPP, okay. Then finally you run the model using the llama CPP or GGML based engine on CPU or Mac, or no GPU is required, means simply we can do the inferencing on the CPU itself. So this is the complete example. I hope with this particular example your understanding is going to be a little more clear. So this is a complete detail of the GGML and the GGUF. Sorry, this llama CPP. You can read it out. Though inside the GGML, guys, we were saving the bin file with this particular name, GGML model Q4 .bin. Okay, and because of that only, this particular library is called the GGML. Now llama CPP, it's again enhancement on top of this library itself, right? So it's a C++ implementation of the on top of the GGML and the on top of the GGML itself, okay, for running the llama family models. So it is providing a CLI, C API, Python bindings and all. So some sort of enhancement on top of the GGML only. Earlier it was only for the C only. Now this is the C++ implementation, which is again providing a Python binding. Okay. Now, guys, if we're talking about the quantization library, like how we can perform the GPTQ quantization, AWQ quantization, right? Uh, how we can do it? What are libraries and all we have? So the first one is the common one, and I think everyone knows about it. It is called Auto GPTQ. All right. So in the Hugging Face also you will see this integration. Then we have this AWQ Python library. I'll come to this one. I'll show you this. Then we have bits and bytes. Okay. Then GGUF, it is a file format. Easily we can convert any sort of a bin file into the GGUF file. I'll show you how. We have a complete script for it. Then GGML, I think we already discussed about it. And then llama.cpp. Okay, I think we have discussed onto it about this llama.cpp and all. See over here. Then we have this tensor RTLM, VLLM, ONX runtime. So this is again some sort of a library of framework. Using this one, we can using this one, guys, what we can do? We can do the quantization. Okay. So the GPTQ, AWQ, bits and byte, GGUF, it's a file format only, but we can how we can convert it. I'll show you. GGML, llama CPP, tensor RTLLM, VLLM, ONX runtime, right? So you need to be like going through with all this library if you want to be like if you want to become a champion in the quantization and all. Then guys, here is the quantization workflow space, so you can again check out. It is the same flow, and here I kept it in the form of table also. Okay. So this thing is very much important. This theory and all I just kept for all of you, and here I explain you the complete concept. Now a couple of things which is remaining. The thing basically it is per channel quantization and per tensor quantization. So here is a per tensor quantization. Now the next one is what? The next one is the per channel quantization. So we need to understand what is the meaning of this per channel and the per tensor. And apart from that, guys, can we perform the QAT and the PTQ inside the LLM? Yes, we can do it, but how? Mathematically, how it is being done? And what all thing we are going to be scale and all means in terms of weight. Okay, how we are doing that, whether we are doing per matrix wise or we are doing layer by layer, means row by row, okay, or column by column. So this thing we need to understand the first place, then only our introduction will be completed and we'll move to the GPTQ. Okay. Okay, guys. So the question is, can we do the PTQ and QAT on LLMs? Yes, we can do it. We have seen the techniques like GPTQ, QAT, right? And regarding the QAT also, Quantize-Aware Training, I'll show you the algorithm and all. But let's see the differences first. Means if we are doing this PTQ and QAT with respect to the simple MLP, and if you want to do it for the LLM, like this a large language model, so what are the differences in between? That we need to understand the first place. Then only our fundamental would be clear. So here the question is, can we do PTQ or QAT on LLMs? So I written over here, yes, we can do it. So post-training quantization and the quantize-aware training are both applicable on LLMs, but the processes significantly change. Okay, significantly model like CNN or MLP means it is a little bit changed compared to the CNN and the multi-layer perceptron, which is also called the artificial neural network. If somewhere someone has written this MLP, what does it mean? The meaning is the artificial neural network. Now PTQ on LLMs. Okay, first let's look into it. So in MLP, we have a simple formula. I think we have seen this particular formula. So what we're doing, guys, first we are doing scaling, and then we are calculating 0 point, okay, 0 point, and then we are going to quantize our value. Okay, then guys, what we are doing, quantize we are quantize our value. Okay, and guys, one more thing. See, we have seen this symmetric quantization, and we discuss about the asymmetric quantization. Okay, asymmetric quantization. Now what's the meaning of the symmetric means if the weight is in a range, let's say minus x to plus x. Okay, so it is in a the this minus value and the plus value would be the same. Let's say I'm writing over here, let's say minus 127 to plus 128. Okay, within this range, if I have to map the weight, or the weight will also be symmetric. Okay, it will be around the 0 only. So 0 will be the center of it. Let's say minus 2.0 to plus 2.0. So this is a weight distribution, and this is a like quantized value distribution. Okay, so in this particular range only we are going to map the value, and here this is a weight distribution. Now in asymmetric, this range is going to be different. This range could be anything. Okay, I hope this all the thing you understood in the previous class itself, in the previous video. Now, if we're talking about this LLM, right? So I written one more point. Done on small tensors, example linear layers can cause, and we can use only this toss.quantization directly. This is the library. This is a module. Okay, this library or this particular module, where we'll get it, guys? So this particular module will get it over the PyTorch itself. So if you will install PyTorch, we can use this PyTorch.quantization. Now, if we're talking about the LLM, so same core inform formula, but with a huge tensor. Okay, quantization is done layer wise, right? Layer wise or per channel. We are quantizing a weight like Q, K, V, feed forward neural network, right? Here we require the small calibration data set around 50 to 200 sample, and it is very sensitive to the precision loss. So see, I written some important points, and these points basically it is with respect to the LLM. So we're talking about the LLM, guys. So see, uh, we're talking about the LLM, which is called large language model. So this large language model is built on top of the transformer. Okay. Now we're talking about the transformer, guys. If we're talking about the transformer, so we have two things. First is called attention layer. The second is called feed forward layer. Okay, feed forward layer. So we're talking about this attention layer, right? If we're talking about the attention layer, so here we have Q, K, and V. So this Q is nothing, it's representing to the query. So we have WQ weight, WQ, okay, Q metric, weight metrics for Q, weight metrics for K, and we have weight metrics for V also. Now, what is the mathematics of this Q, K, V? That's a different discussion. Okay, all sort of a different discussion. We'll do it in a different session when once I'll explain you about the transformer model, right? So we have this Q, K, and V. So guys, feed forward is nothing. It is the same. It is called MLP, multi-layer perceptron. Okay. Now, if we are going to quantize the weight of this attention, means this WQ, WK, and WB, and if we are going to be quantize the weight of this feed-forward neural network, see, we can do it directly. Okay, with the same technique like we have earlier for the simpler MLP, CNN, and the normal RNN and all. But guys, this model actually is very huge. If we're talking about the size of this model, so this model actually it's going to be very very huge. Means the weight, okay, weight and biases value will be so many, right? And there will be like a millions and billions of parameter, millions and the billions of parameter you will get inside this LLM. If we're talking about the parameter, guys, what is a parameter? Parameter is nothing, it's the weight and biases only. Okay, so guys, if we are going to be quantized, let's say we have this WQ, right? If we are going to be quantize this WQ, let's say this is the matrix, WQ matrix. If we are going to be quantize this WQ matrix directly, okay, the complete matrix in a single go, okay. We are going to be we are going to be quantize this complete matrix in a single go. You know, guys, this will not be having the good impact. Means uh, subsequent metrics will be associated with this one. Subsequent metrics means what? We don't have only one block inside the transformer. If we're talking about the transformer, guys, in the in the base transformer itself, we are having 6 subsequent block. Okay, 6 subsequent block. So guys, this WQ, right, it is associated with the other one. Then that it is associated with the other one, and the size of it, it's not going to be very simple. Means 2 cross 2, 3 cross 3. It is having a very huge size. Okay, the token embedding which we are doing, so it is around 5121024, something like that. Okay, maybe more than that. Okay, in the state of art embedding model. So guys, we cannot quantize this complete model in a single go. It's not going to be show too much impact. Okay, so what we do, instead of quantizing this complete matrix in a single go, we quantize the layers, means first row, second row, third row, and then we check, guys. What we do, we check Okay, what is the impact of this first row quantization, then second row quantization, then third row quantization? It's an iterative process. Okay, it's an iterative process, and this is what this GPTQ is doing. You know, this is what this GPTQ is doing. So whenever we're talking about this LLMs, so in the LLM, you know what we are doing in a LLM, guys? We are going to perform the per channel quantization. Okay, it is not per tensor quantization. Per tensor quantization we do in normal MLP, in a normal and CNN, in normal LSTM on the RNN. But guys, if we're talking about the large language model, in that we perform the per channel quantization, right? So this is a complete theory which I written. Let's try to deep dive into it. If we're talking about the tools, okay, tools for the QAT on LLM. So we have this Torch.io, Intel Neural, NVIDIA Tensor, OpenVINO, HQQ, Smoother, Quant and all. If we're talking about the QAT, guys, so it is what? It's a quantize aware training. Okay, it is quantize aware training. Means at the time of the training, we are going to perform the quantization. Got it? Now, guys, here you can see this is all about the PTQ, okay, in LLMs. Now, tools for the PTQ, I think GPTQ, AWQ, Auto GPTQ, bits and bytes, we have already discussed about it. Now, if we're talking about the QAT, so you have seen in the previous session, we're talking about with respect to simple MLP, multi-layer perceptron. So we are using this quant stub and the dequant stub technique to simulate the quantization operation. Fake quantization during the training and the backpropagation through the quantization operation will minimal overhead, right? So this was a complete technique of the QAT. If you don't know about it, you can check out with the previous video. I discuss it in a very detail. Now we're talking about the LLM, guys. So in LLM, this QAT technique is very complex and expensive. Okay, because it is directly associated with the training, and you know the training the training of the LLMs, right? How expensive, how painful it is. So guys, we generally don't go with this QAT technique in terms of this LLM. We always perform this PTQ technique only, GPTQ, QAT, right? GPTQ and the this one. What was the second one? AWQ. Okay. Now you can read it out this particular points what I have written. I have written much more complex and expensive because here the training is associated. You simulate quant ops using STE, straight through estimation, requires full or partial retraining of the model, requires multi GPU or TPU setup because here the training is associated. If we are going to perform the training of the LLM model, so the training of the LLM model is very expensive, guys. Okay, very expensive. So in simple MLP or in simple CNN, that was fine. Means we can afford it, right? But in a huge LLM, Mr. Llama, GPT, or DeepSeek and all, it's like very expensive. Okay, so we don't go for this particular technique. Now these are all the libraries which we can use to perform this QAT. Still like some work and all is going on in a community. Okay, this researcher, open source developer, open source contributor are doing this QA and all, and they are publishing some research paper. They are publishing some GitHub repo, and they are publishing their model over the Hugging Face and all this QAT models. I'll show you those one. I'll come to that one. Okay, while I'll be doing a practical and all. Now here you can see component nodes. So activation quantization. So it is a challenging due to softmax layer norm and tension. Weight quantization done QKB FFN means feed forward network, often with per channel granularity. Then techniques dynamic, static, and fuse quantization technique are often combined, right? So these are some topic these are some point as I will go ahead with the GPTQ and this AWQ. We'll discuss onto it. Now here is all the summary, guys. So if we're talking about the PTQ, it is easy. We can do it with the torch quantization with respect to MLP. But if we're talking about the LLM, so layer wise need calibration, and we are using this GPTQ or this AWQ. Now we're talking about this QAT. So it is a light training in MLP, but it is a heavy retraining in the LLM. Okay. Now activation handling simple. Now here it is little difficult, complex. Now tools wise, guys, so it is having a built-in torch tools, means using the torch tool only we can do it. And if we're talking about this LLM, guys, so we have the GPTQ, okay, AWQ, bits and bytes, torch IO, tensor RT, LLM and all. With that we can do. Hardware needed, single GPU is fine, multi GPU and TPU will be required for the large language model. So this is some differences, guys. For sure you need to be you need to read it, you need to go through with it, and you can clearly understand this PTQ, QAT, activation handling tools, hardware and all with respect to simple MLP and the LLM only. Now coming to the next topic, which is the last one. So what is a per tensor quantization? Okay, so per tensor quantization means what? Definition. What's the definition of it? The entire tensor, okay, the full weight matrix, share a single scale and the 0 point. Means in a single go we are going to be quantize this complete matrix. Okay, so use case simple and faster, often used for the activation, but less accurate. Specifically different channel have different value range. Okay, different channel means what? If we're talking about the channel, guys, this channel is representing the rows. Okay, rows, either rows or column. So we're talking about this channel, so that doesn't mean like it's a different kind of channel. It is simple row or the column. Generally we talk about the rows. Okay, so imagine you have a weight tensor, the size of it 4 cross 3. This is my matrix. Okay, matrix itself is called array, tensor, whatever you can say. Tensor basically in terms of the deep learning, because we are going to be executed over the GPU, and GPU only takes the tensor. Okay, it is a special array which have been designed for the GPU processing, right? So here you can see we have the first row, second row, third row, and fourth row. So in a single row, we are going to be quantize this entire matrix. Okay, so in a single go, we are going to quantize the entire matrix. So for the entire matrix, we will be having one scale value, and we will be having 1 0 point. Okay, 1 0 point. So this type of quantization we do where this per tensor quantization we do with respect to the MLP, normal MLP, normal basically CNN or RNN. Okay, and this is the second one is called the per channel quantization. So this specifically is for what? This per channel quantization is specifically for the LLMs. Okay, so here you can see I kept the definition of it as well along with the example. So per channel quantization, this is specifically for the LLM. So each channel, each row, okay, in weight matrix get its own scale and the 0 point. Okay, it is used mostly for weight in CNN and LLM. So if we're talking about the huge CNN, like ResNet, DenseNet, okay. So for this ResNet, DenseNet, we are going to be use the same technique, and in LLM also. LLM means what? LLM means I think we already know Llama, Mistral, GPT, okay, DeepSeek. So these are some famous model. Cloud A model, Opus, right? Or Sonnet, Gemini model. So these are some famous model, or Grok is also there. Okay, you can like check out with the name or like there is a huge list of the LLMs nowadays. Okay, but these are some famous and good model. Now specifically useful when each channel has a different range of the value, because this LLM is very huge, and uh, this each and every row could have a different distribution of the weight. Okay, the range of the distribution. So using same metrics, but here channel wise, row wise, we are going to perform the quantization. So we are going to calculate a scale for this row, this row, this row, this row, and separately we are going to perform the quantization. So per channel quantization we do inside the LLM, and per tensor quantization, per matrix quantization we do in the simple MLP and the CNN, means inside the small model only. So here guys you can see the complete differences in between. So in per channel quantization we compute 4 different scales and 4 0 point. I think I already discussed it. So we have 4 different row. So we are going to be calculate 4 different scale and 4 0 point. Now this is the complete differences. So per channel and per tensor and per channel. So it is having single scale and 0 point. It is having one scale and 0 point. Now it is faster, it is slower, it is lower, it is higher accuracy wise, and use case, activation, and the weight specifically in LLM and the CNN. Okay, now guys, here you can see the complete summary of it. So LLM mostly use symmetric plus per channel quantization, okay, for the weights. Now CNN or activation might be used, CNN and activation might use asymmetric per tensor quantization. I mean, this is for the small model, small CNN and MLP, and this symmetric and the per channel quantization for the huge LLM. Okay, now I hope guys you understood this entire thing, and yeah, this notes is helping you a lot. Once you will go through with it, you will be able to understand the entire uh, concepts. Okay, whatever concept is all, whatever concept and all I have mentioned over here. So yeah, this is it, and so yeah, I will come to the GPTQ now. Then we'll discuss the practical of it. Okay, GPTQ, then AWQ, then QAT, and then final GGML and the GGUF. Okay, so guys, let's start with the GPTQ. So this GPTQ I divided into the multiple parts. In the first part, we'll discuss what is a GPTQ. In the second part, we'll discuss what is the difference between this GPTQ and the normal PTQ. Then we'll come to the mathematics of the GPTQ, and then finally we'll see the practical implementation of this GPTQ. So let's begin with the GPTQ itself. I think you're already aware about the definition of it. So GPTQ means what? Gradient post-training quantization. It's an advanced post-training quantization method, okay, which is specifically designed for the large language model. Okay, so here I mentioned couple of large language model name. The first one is a llama, right? The second is GPT, Mistral, Falcon. We have hundreds of large language model. So for all those large language model which was implemented using the transformer was architecture, if you know about it. So this GPTQ method is specifically designed for the transformer based model. Okay, now guys, here it is trying to quantize a weight. Okay, it is trying to quantize a weight in a lower precision. I think you know about the lower precision, the higher precision. If you don't know guys, you can check out with my previous video as well. There I discuss in a very detailed manner. Now guys, here in this GPTQ we don't require any sort of a training, because the name itself they are saying it's a post-training quantization, means first we'll do the training and then only we are going to perform the quantization. Okay, now let's discuss some characteristic over here. So characteristic wise, advanced PTQ method using the gradient based optimization. It is an advanced PTQ method using gradient based optimization. So we'll discuss this specific term. What is this gradient based optimization? This might be new for you. The second is a design is specifically for the transformer, which I already conveyed. Target int 8 int 4 quantization for the model comparison and for the faster inferencing. Guys, remember this part because this is very much important. And if someone is going to ask you that why we use the GPTQ, you can simply say we use it for the faster inferencing. Here the training is not required. Even after the training we can perform the quantization of the transformer based model like the large language model. Okay, now training is not required, which I already told you, right? Now what does GPT mean here? GPT means gradient post training quantization. So few people are saying GPT means it is like inspired from the GPT model. Yes, it is inspired from the GPT model. It is for the GPT model, but here this GPT, right? GPTQ. So what this GPT is standing? GPT is standing gradient post training quantization, because this method is relying on the second order information. What is the second order information? Second order information means gradient of gradient, right? So I think you know about the gradient. If you know about the machine learning, if you learn about the machine learning, so in the machine learning we have a very famous term. The term is called the gradient descent. Now what we are doing inside the gradient descent? So inside the gradient descent we are trying to differentiate the loss function with respect to the weight. Okay, so after this one what we are doing, we are going to calculate the gradient, and gradient is nothing. Gradient is representing the slope. Okay, and if we are if we're talking about the slope technically, so it is nothing. It is a very minute difference on a point. Okay, on a point. Okay, this point could be anywhere in the xy space, xyz space. It's a concept of the mathematics only, right? So with this gradient, with the help of this slope, we can check the rate of change. Okay, and if you want to know more about it, definitely you can check out with the gradient concept. You can check out with the derivative concept, or else I will record some video on top of the ANN, artificial neural network. There we can discuss about this gradient descent and all. Okay, it's a very important concept of the artificial intelligence. So guys, here GPT means what? GPT means gradient post-training quantization, and sometime you will say it is a GPT quantization. And you can check out the research paper also once you will go and check with the Google. So directly you will get the research paper of it. You just need to write GPTQ research paper. Okay, so let me write over here research, REARCH research paper. Okay, so guys, you can check out with this archive link. So over the archive website you will find out the paper, research paper of the GPTQ. So it is saying accurate post-training quantization for the generative pre-training transformer. Okay, So the method basically, this method specifically have been designed for the GPT model only, and the technique which they are using, it is a gradient based technique. Okay, it's a Hessian matrix based technique. It's a second order gradient based technique. Okay, if you want to know more about this thing, so definitely you can check out with this research paper. Otherwise, you can read the abstract and all over here. You will get the enough amount of information. Okay, so let's start the differences between the GPTQ and the normal PTQ. So normal PTQ we have already learned in the previous video. Now let's try to compare both. Like what is the differences and how basically this GPTQ is different from the simple PTQ. So here guys, all the differences between the GPTQ and the PTQ. So first, let's see some theoretical point, and right after discussing this one, I'll show you some mathematical formulas and all, and then we'll look into the practical. So post-training quantization usually replace full precision weight with the lower precision, as we know. So if you will check with my previous video, so there I already discussed, if we're talking about the post-training quantization, that is PTQ, there what we are doing. So after the training, whatever model we are getting, so in a model, let's say the weight belong to FP32, or the weight belong to FP16, right? FP16. Now we are going to replace these particular weights with the lower precision, that is int 8 or int 4, right? Int 8 or int 4. That's it guys, right? Now guys, just think, we have replaced the weight. Okay, are we tracking the error, like how much loss we are getting? So after replacing the weight, definitely there will be some sort of a loss, right? If you know about the feed forward neural network, or if you know about the artificial neural network, so what is happening over there? So there actually we are trying to trying to calculate the output of the header layer. That is nothing, that is a w multiply x, okay, and then we are passing this particular value to the activation function, right? And if we have multiple neurons, then we are doing summation of it. So this is a complete formula. Now guys, at the end what we are doing, so at the end we are trying to calculate a loss between the actual value and the predicted value, okay, and we're trying to minimize this particular loss with the back propagation. So in the back propagation we have a different optimizer. Now we are using this particular optimizer and trying to reduce the weight, we are trying to reduce the loss, okay. Now guys, whenever we are changing our FP32 FP16, so definitely there is some sort of a loss, okay. But how my quantization algorithm will get to know about it? So there was no such mechanism in the older PTQ method. Now this GPTQ basically what it is doing is trying to navigate, okay, it is trying to navigate to the entire it's trying to navigate to the entire layer, and whatever output is being generated at the end, on behalf of that particular output, whatever loss we are getting, it's trying to understand that particular loss, and then only it's adjusting the weight, okay, then only it's trying to adjusting the weight from the higher precision to the lower precision. So in short, you can say this GPTQ is nothing, it's a very smarter technique. So it's a smarter technique compared to the normal PTQ, because it's trying to check out the loss, okay. It's not only quantizing the weight. The end goal of the GPTQ is just not just to quantize the weight. Apart from that, it's trying to check out the loss as well, okay, and behalf of that it is taking a decision what should be the final quantization. I hope you are getting my point. Now let's do one thing, let's try to discuss some theoretical points. So here guys, you can see I kept each and everything for all of you. So post-training quantization usually just replace full precision weight with a lower precision, right? It focus on minimizing the differences between the original and the quantized weight. That's it. But this does not always ensure that the model final output remain close to the original output. Means it is just trying to check the differences between the original weight and the quantized weight. That's it. That is called the quantized error, which we have learned in the previous class. Okay, but here guys, it is not going to be estimate what will be the impact of it over the final output. Now GPTQ is smarter. So what it is doing guys, so it is tracking the error that quantize introduced in each layer, okay, not just at the weight level but also affect model's output. the same thing which I told you. So here guys, what is doing, whatever output we are getting, okay, and then after getting the output, whatever loss we are having, so based on this particular loss only, it's trying to detect, okay, so what should be my final quantization. It's trying to adjust the quantization. Now it is using the second order information. Second order information means what? Second order information means we are trying to perform the gradient, we are trying to calculate the gradient, and on top of the gradient again we are trying to calculate the gradient, okay. So that is called the second order information. Now why we do it, we'll talk about it. This is also called the Hessian approximation, okay. So it's trying to understand the sensitivity using the second order gradient, or it is also called the Hessian approximation, which weight are more important for the model performance, okay. GPTQ then selectively quantize weight in a way that minimize the final output error, not just weight wise differences. So guys, the concept is very simple. Let me summarize all the thing for all of you. So whenever we're talking about the PTQ, so what this PTQ is doing, so PTQ is trying to check the so here is my weight, okay, that's trying to quantize the weight. So it's my quantized weight, right? Now whenever we perform the dequantize, right, so here is my weight, dequantized weight. Now it will check the differences between the dequantized weight to quantized weight, and it will just estimate this particular error. But guys, this is not a sufficient one. In short, I can say it is not a complete one. So whenever we're talking about any sort of a model, okay, in the model the output matters, okay, and always we try to minimize the loss, right? And for minimizing the loss we use some gradient based technique, and GPTQ follows all those GPTQ follows all those weights. At the end it's trying to detect the loss, okay, and behalf on that only it's trying to adjust the weight of the model. So the idea is very simple. Not only check the quantized error as well as check the loss, okay, and then only decide the final weight. So guys, here is the differences. You can simply read all the differences. Now let's try to go through it one by one, and let's try to read all the points over here. So guys, differences is also very simple. Let's try to discuss it one by one. So the goal is, what is a goal? So the goal is simple, to quantize the weight. So whether it's a normal PTQ or it's a GPTQ, right? So we are in both techniques. In both techniques we are trying to reduce the precision of the weight. Formula. So here is a formula. I think you know about the formula. You are aware about this particular formula if you have seen my previous video, the first part of this LLM quantization. This is a formula of the GPTQ. So what it is trying to do, guys, so here you can see it's trying to calculate output of the hidden layer with the normal weight. Then it's trying to calculate output of the hidden layer from the quantized weight. This WQ, normal W is normal W without the cap, it is representing to the normal weight, and W cap it is representing to the quantized weight. Then we are trying to check the differences in between, okay, and we are trying to reduce it, we are trying to minimize it, okay. So this is the whole sort of idea of the GPTQ. We'll discuss in a detail in the next slide. I kept the entire formula in the example. So here is a level, guys. Level mostly tensor wise. So we are trying to perform this PTQ tensor wise. Sometimes we also do channel wise, but guys, this GPTQ is completely channel wise. Okay, in the previous slide itself, in the LLM quantization introduction, I discuss about the per channel quantization, per tensor quantization. If you're not able to recall it right now, then please rewind the video and check over there, right? So guys, if we're talking about the level, so don't forget about this channel wise over here. This GPTQ we perform on a channel wise, right? What is the channel wise? So we perform it on a particular column or particular row, right? We never perform it on the entire tensor. We do it in a smaller model like normal ANN and all, but if we are talking about a transformer based model, there we never do it. We always go channel wise, okay. Now error awareness. So here guys, you can see no modeling of how quantization affect final output. Here we use the Hessian, okay. So here guys, I told you no modeling of how quantization affect final output means we are just trying to check the error between the quantization and the dequantization weight, that's it. But we are not like even checking the we are not even checking the quantized weight relation with the output. Now here guys, we are using the Hessian technique, which is the second order gradient. We'll discuss about it, what is the second order gradient and all. Error compensation, no. Yes, there it gives you the error compensation. What is the meaning of it? So it adjusts the quantization to compensate the future layer. So it's trying to improve, okay, layer wise layer. That is called the error compensation, and yes, in a GPTQ we'll get it, because at the end we have to minimize the loss with respect to the quantized weight. Then calibration data, we don't use the calibration data. Generally we use the calibration data. If you don't know about the calibration data, then again rewind the video or check out the first part, you will get to know about it. It's just a sample data which we are using just to quantize, just to calculate some value. Okay. Math, it's a basic linear scaling. Now here it's a linear algebra, which is metric decomposition, second order gradient and all. So it comes under the linear algebra and the calculus, right? Then LLM use case, no, we don't use it in a LLM. We use this is specifically designed for the LLM only, right? So these are basic differences between the normal PTQ, which we have learned in the previous video, and here we are talking about the specific GPTQ, right? We specifically designed for the LLM model. Now let's try to discuss couple of terms. So metrics approximation, what's the meaning of it? The meaning is very simple: replacing a larger complex metric with a simpler version. Okay. Method, low rank method. So we are trying to, which method we use for the metric approximation? You can use this SVD method, single value decomposition. Okay, we can convert our higher value higher ranking metrics into the lower ranking metrics. Purpose, reduce memory and the acceleration computation with the minimal accuracy drop. Okay, so metrics approximation means replacing a larger complex metric with a simpler version. Okay, now why we are doing it? So that we can increase the speed and with a minimal loss. Now here calibration data. So here I given the definition of it, you can read it. Now Hessian means metrics of second derivative. Now what is the first derivative, guys? Let's say here I'm writing dx by dy. So this is the first derivative. Now again, if I am doing derivative of it, let's say dy by d of dx divided by dy. So this is what, this is a this is called the second derivative. Means again we are doing derivation of the derivative value. Now in the first derivative, you always capture the slope, as we know, right? Let's say we have any graph and any basically graph over here in the x and y. Now over this point we are checking the rate of change. Okay, we are checking the rate of change at this particular point. So this is what, guys, this is the slope, right? Now what we can do, guys, we can check the curvature also at that specific point, and for that only we use the second gradient. This is all the mathematical formula. Now here see, guys, this is the slope. Okay, so generally we calculate the slope, we calculate the rate of change, right? Like how much y is changing with respect to x using the derivation only. So this is a complete concept of the derivation. Now if you're talking about the second derivative, second degree derivative, in that case we are calculating curvature. So here we are calculating slope, okay, the rate of change. Now here we are checking the curvature, okay, at this particular point. That's it, guys. So these are differences. Now let's see the practical and the mathematical formulas and all along with the example. Now guys, let's understand the core idea behind the GPTQ mathematics. So guys, GPTQ treats quantization as a metrics approximation problem. So what is this metrics approximation problem, and how basically we can quantize a weight using this metrics approximation problem? We'll try to see the entire derivation. I kept the solution for all of you. Okay, so here guys, you can read this particular line. You are replacing the original full precision weight matrix W with a quantized version. If you know about the weights, guys, so the weights you will get in a attention layer, the weight you will get inside the feed forward neural network, means inside the neural network. I can give you the glimpse. So let's say we have an input layer. Now after the input layer, guys, what you will get the hidden layer, right? So this input layer and the hidden layer is connecting to each other with the weights, okay, with the weights, and then finally it will go to the output layer. So this hidden layer and the output layer, again between that you will find out the weights. Okay, so
here you will see the size of the weight matrix, so it would be 3 cross 2, right? And here if you will see the size of the weight matrix, so it will be 2 cross 1, right? There will be 2 weights, there will be in total 6 weights. Okay, so this all the weights, right, is being replaced by the quantized weight. Now, given a large matrix with a higher value precision, can we find a similar metric with a lower precision that produce nearly the same result when we use in a computation? Yes, that is the main idea behind the GPTQ. Means we have a higher precision number, higher precision value, and we are going to convert into the lower precision value. So I kept one more example, as you can see here. So we have an original matrix. So in the original matrix, you will find out weight something like this: 2.743, 1.879, right? So this is the higher precision value, right? This is the higher precision value. If you don't know about the higher precision, the lower precision, you can go and check out with my previous video. There I discuss almost all the thing with respect to higher precision, lower precision and all. Now a quantized matrix. So guys, whenever we'll get a quantized matrix, we will get weight like this. So this is the lower precision value. Okay, we are not going to store the exact information about the weight, right? It is a approximate value. It is a lower precision value. So we are going to convert this to this to this to this, like this. This is just an example. Now what is the objective, right? What is the objective behind the GPTQ? So the objective is minimize the output differences caused by using W cap instead of the W. So W cap is representing to the quantized weight and W is representing to the original weight. So this is my objective, guys. Wx it would be same, it would be equal to, okay, it will be approximately same to this W cap multiplied by X. Okay, so in short I can say we are going to quantize a value, but the output would be the same one. Now here you can see the annotation, right? This W is representing the original weight matrix. This W cap is representing the quantized weight matrix. This X is representing to the input activation. Now what does it mean? So let me explain you again with the example. So let's say we have a neural network. Okay, everything I'm explaining with the neural network, but guys, this same concept will be applicable on the attention as well. If you know the transformer, let me talk about that as well. So guys, if you know about the transformer, in the transformer what you will get, in the transformer you will get one block, right? Now inside this particular block you will get mainly two things. The first thing is called the attention block. So this is your attention block, and the second block will be the feed forward neural network, right? So this is the attention block. Let me write over here attention block, and here this is my feed forward neural network. Okay, now in both architecture, in both network, I would be having the weights. Okay, so here also you will get the weights, and here also you will get the weights, right? So we are going to play with these particular weight matrices. I hope now you're getting a clarity. So original weight matrix, WQ means quantized weight matrix, and X means what? Input activation, means after the activation, after applying the activation, input activation means what we are going to input into the activation function. So here let's say we have our input layer, then we have a hidden layer, okay, and then this is my neural network, right? Now here we'll pass this X input. X is representing to the input, W is representing to what? Weights. Now this particular value we are passing to the input, to the activation, right? So input activation, so here X multiplied W, so this particular value we are passing to the activation function. This could be the this could be any activation function, okay, it could be the sigmoid, it could be the 10H, it could be the softmax and all, right? So here this and this, right? X means input and W means what? W means weights. So we are going to replace this particular weight with a quantized weight, okay, and this particular value, the entire value, we are passing to the activation function. So it is representing the same thing, as you can see. I hope this entire formula is clear. Now what is the outline? So outline is very simple: original weights to the quantized weight to the output compare. Now this is the complete step, guys. Linear output. So we have output like this: y x w t. Okay, this is nothing, it's a multiplication between this input and the weight matrix. Now this is my loss function. Okay, we are checking the differential between the original value and the quantized weight. Okay, then Hessian row wise. So this is my Hessian, this is one more step Hessian, I'll come to that. Now quant error estimation. So here we are going to estimate the error. Okay, then error compensation. So how much error we are going to compensate, right? How actual output we are getting at the end. That is my main objective. So this is all the step, guys. Now we'll try to understand this each and every step with the entire derivation. Okay, with the values. So guys, let's understand the summary of the entire flow. First, we are going to compute the original output. Now after computing that, we are defining a loss, okay, because this loss only we are going to minimize in future. Now what is the loss? The loss is nothing, it's the differences between the original weight as well as the quantized weight. Means whatever final output we are going to be calculate now with the original weight as well as the quantized weight, the differences, okay, the differences we have to minimize. Then we are going to compute the Hessian. Now what is this Hessian? So this tells us how sensitive output is to change in the weight. Now whenever we are going to change the weight, now like how sensitive it is with respect to the output. Okay, then use that to quantize weight while minimizing impact on output, and apply error compensation to maintain the global accuracy. Means the moral of the story is very simple. We just have to quantize a weight in such a way so that is not going to be reduce the overall accuracy. Now calibration data, I think you already aware about the calibration data. GPTQ required a small set of real input to simulate the real inference data. Okay, this helps to compute to quantization more accurate. That's it. I think in the previous video also I shown you the use of this calibration data. In today's implementation also I'll discuss about this calibration data. So here is the entire here's the entire derivation, guys. So one by one, step by step, let's take a look onto this derivation and let's see how basically the quantization is happening. Okay, now let's see the example. Let's see the step by step process. So first we are going to compute the output. So here I took one example, guys. Let's understand with this particular example. So what I have this input. So this X is representing to my input, this one. This is my weights. Okay, I can write here input, and this is my weight. Now this is the multiplication between what? Between this X and W. Okay, and here is what? Here is my output. Now this is my main culprit, guys. Okay, this weights. I need to update this weight. Okay, I need to quantize this weight. I need to quantize these weights. Okay, so here, guys, see how this entire process is working, how the GPTQ is working. We need to focus on that part, right? And how this GPTQ is able to give us a best to best quantized weight. We need to focus on that side. So if you are aware about the basic multiplication, the metric multiplication, the neural network, I think usually you can understand this particular operation. If you don't know, then I think I can show you with the diagram. So X, right? How many rows we have? 1 and 2. So in rows, how many inputs we have? 1, 2, 3. How many columns we have? This columns basically it works as an input. So 1, 2 and 3. So from here the rows will go. So let's say here is my first row. Okay, first row means what? First row means this one, 1, 2, 3. Second row means 0.5 minus 1.0 and 2.0. So my values will come from here, and then it's going to be connect with the next layer. So in the next layer we would be having 2 neurons. Okay, 2 neurons. So here is what? Here is my neural network, as you can see, guys. So how many weights we have? We have 3 weights, 3 set of weight. Okay, this is for the first one, this is for the second one, and this is for the third one. Okay, this is for the third one. So 0.1 I can write over here. Let's say 0.1 and minus 0.4 minus 0.4 for this first node. Thus for the second one 0.2. Okay, and then 0.5. Then for the third one 0.3, and then 0.6 like this. Then I'll be getting my output. So my output will be like this. This is my output. So for the first row, I'm getting this output minus 1, sorry, 1.4 to 2.4. And for the second row, for this one, I'm getting this output 0.4 to 5 to 0.5. So I'll be getting two output over here, guys. One for the first rows and second for the second row. I hope this entire thing is clear, like how this neural network is working. So what is the explanation behind this step? So explanation is quite simple. This is a basic this is a basic forward pass in a linear layer. You take input activation and multiply them with the weight matrices. The output Y is what the model predicts before the quantization. Okay, the output Y is what? The output Y is what the model predict before the quantization. Means so far we haven't done the quantization. Now we'll do the quantization, and after the quantization, whatever model you're going to be predict, so we are going to compare it with the natural or the normal value. Okay, now let's see the quantized goal. What is a quantized goal? As I told you earlier as well, so we want a quantized version W hat such that loss should be this one. Okay, loss function should be this one. So here mode of square is a Frobenius norm. So guys, it is a fancy name. If you have learned the machine learning, if you are aware about the deep learning, the basics of the deep learning, I think you know about the sum of squared. Sum of squared, how it is working? X2 minus x1 square plus y2 minus y1 square, right? Z1 Z2 minus Z1 square. Okay, and then we check the root of it. So this is called sum of squared. Okay, root mean sum of squared. I think you already learned these formulas and all in your machine learning or in your deep learning. Now here guys, you can see, so the loss is a minimized over the row W one at a time. That's why GPTQ row wise quantization. Okay, that's why GPTQ is a row wise quantization. Why? Because on a row wise we are going to calculate this particular loss, and with the optimization technique we'll try to improve it. Okay, with the optimization technique we'll try to improve it. So guys, here this line is very much important. This is why GPTQ is called the row wise quantization, because this loss, okay, which we are going to be calculate for minimizing, it is for row. As and I told you, per row quantization, per channel quantization, everything I explain you already. So let's see the explanation over here. So the explanation is very simple. So you are comparing the original output, okay, with a quantized output. The Frobenius norm just means sum of squared error. Goal: find W cap, quantize weight that make this difference as small as possible. So here what is our goal? The goal is very simple. We have to find out the W cap. Now this is my quantization weight. Okay, and we need to figure out this quantization weight so that we can reduce error as much as possible. Okay, we can reduce the error as much as possible. That's the main aim over here. But the question over here, where's the quantization weight? How we'll get the quantized weight? We're saying quantized weight. We are looking into each and every part, right? How the GPTQ is being performed, the training, what was the weight, the size and all. But how to get those quantized weight? That's the main thing. So let's follow this particular step. So take one row. How to get the quantized weight? You will get it inside this particular step. Take one row of weight, compute output using real-time input data, tries or all possible 4-bit value for each weight. Okay, measure which rounding caused the error least, pick a smart quantization value and compensate in the next row for any introduced error. So guys, I think you know where is this weights. So this is a very advanced technique guys, this GPTQ. Inside this technique you can see for getting this quantized weight, okay, and to make this weight as better as possible, okay, make this weight as good as. So for that what we are doing kind of training. Okay, there's not an actual training what we are doing, guys. So here we are checking, right? We are checking what is a error, how much is a error on a row basis. Okay, and then we are improving on top of it. So take one row. Okay, so let's say if I want to be update of this, if I want to update this particular weight, so what I'll do, I'll take first row, this particular row. Now after taking this row, after taking the first row, okay, what we'll do, will compute output using the real input data. Okay, that's fine. Tries all the four possibility. Try all possible 4-bit value for each weight. Okay, so let's say if we're talking about the 4-bit, so whatever range would be there with respect to these particular data type, let's say the range is minus 128 to plus 127. So we're going to check all the value between this particular weight. Okay, try all the possibility between the given range. Measure which rounding caused the least error. Now we have to figure out which value is going to, like, which value is going to be generate a least to least error. Okay, I hope guys you got it this thing, and it is very easy to understand, but very typical to imagine the entire thing. But don't worry guys, as you will read it again and again, you will be able to get that. Now let's understand about the Hessian matrix and the approximation. Now guys, let's understand the Hessian matrix approximation. So to preserve the model output better, GPT incorporates second order error correction using the Hessian matrix. So what is this Hessian matrix? So Hessian is nothing, it's a gradient of gradient. Let me write over here, gradient of gradient. Okay, it's a second order derivative. So how to write that? If we're going to calculate the gradient, so it will be something like this, del L by del W. Now the second order derivative would be del square L del W square. So we are going to again perform the derivation of the del L. Okay, we are going to perform the derivation of the loss function. I can write in such a way also. So del by del W. Now here I would be having this del L and del W. I hope guys this thing is clear to all of you. Now, so let's take the one line summary. So Hessian and GPTQ is a smarter tool to identify which weight are risky to quantize. So GPTQ can do it safely without messing up the output accuracy. Okay. Now what we are doing guys, we are passing real input, compute Hessian approximation, get sensitivity per order, do the safer quantization. See, when we perform this derivation, so we perform this derivation after the loss, means first we are performing the computation. Now after performing the computation, we'll calculate the loss. Now after calculating a loss, what we'll do guys, so after calculating a loss, we'll perform the gradient, right? Gradient. Now if we're going to calculate the gradient of gradient, so that is called Hessian. But this Hessian approximation we calculate using this x transpose this input transpose x. Okay, so here we are going to perform the dot product, x transpose dot x. Okay, so this is called the Hessian approximation. Don't worry, I'll show you the output and all, how what output I'll be getting and how we are going to check whether this weight is correct or not. Okay, whether this weight is correct or not for the quantization. Okay, means for the further calculation and all. Now let's look into few more points over here. So this is a covariance metric. The metric which you can see, it's a covariance metric. It's a concept of the statistic. If you know the statistic, I think easily you can understand this particular metrics. Okay, so this is a covariance metrics. It tells us which direction in W are more sensitive to change. Okay, this is a second order metrics used for the error sensitivity. It tells us if I make a small changes in a weight, how much does the output change. Okay, now here guys, you can see we compute this for each row of weight, hence row wise, as I already told you. So whatever row we are passing in neural network, so with respect to that particular row, okay, corresponding that row, we have a weight. The weight is assigning right between the input layer and the hidden layer. So we are going to be calculate these particular value for each and every row. Okay, so GPTQ is a row wise quantization. Okay, per row per tensor. I think already I discussed this particular thing. Now here is all the step. You can read out this particular step. It's just a summary. So take a real input, then perform the this Hessian approximation. This will give you the value telling us how sensitive output is how sensitive output is to each weight. Okay, GPTQ uses to choose safer quantization value. That's it, guys. If someone is going to ask you in an interview, then please explain at least this much. You can easily clear the interview, okay, with this much of knowledge. Now the next topic is the quant error estimation. The second is the last one is the error compensation. So let's understand about the quant error estimation. So here is my W, then W cap. Now here what we are doing, guys, we are going to check the error, okay, in between. And guys, here we are going to check the sum of squared, right? So this is not this is not an absolute value, it's a sum of squared value. Means we are going to be check it for the multiple weights, okay, whatever weights is there in the matrix, and this is the Hessian value. I will show you with one example. I kept the entire matrix and all. I can show you the entire calculation, okay. Then here you can see the explanation. So W is a real weight, W cap is a quantized weight, is the square of the quantization error, multiply by h. This tell us how important this quantized error is and how much it impact to the final output, right? As I told you, it's going to be check the sensitivity of the weight and in which direction the weight is going on. GPTQ uses this to decide which way to quantize more carefully, right? Now error compensation. So here W dash, okay, so is equal to W minus correction. So here you can see the explanation. Once a row is quantized, some error is introduced. Definitely there will be a little bit error. GPTQ compensate future row, right? So let's say we have a multiple rows in the data. In data I have 3 rows, okay, 1, 2 and 3. Now how many columns? So let's say we have 1, 2, 3, 4 column. Okay, so I'll pick this particular row, okay, and I'll pass in my network. I'll pass where? In my network. Now after passing in the network, what I'll get some error, okay. So W minus W cap. So I'm going to calculate a error. So here my error will be calculated. Now, so error compensation. Now whenever the next row will be passed, so I'm going to be compensate the error. Now how much correction we have to do in this specific weight? So the W cap or W dash would be W minus correction. Now this correction basically it will come to the previous row. Okay, we are going to be calculate this correction and all. Now see, once a row is quantized, some error is introduced. GPTQ compensate future row by slightly adjusting their weight. This is called error propagation. W cap is the new corrected weight used in the next step. I think you are getting my point. So first we are going to quantize a weight. Then whenever we are passing a new row, okay, so this correction value would be there. Now we are going to be use this correction value and then we are going to finalize our weight, okay, for the entire calculation. So guys, this GPTQ seems complicated in terms of the mathematics, but if we are just understanding couple of points over here, okay, what is the calculation now, how it is going to be calculated, the Hessian matrix, then after the Hessian matrix, what is the quantized error, then error compensation, I think will be good to know, okay, will be like good to explain to anyone in the interview. So this is my motto, okay. Now this is fine. I think like if we are going to explain this much in an interview, that would be great, and then rest of the focus will put in the practical, okay. So now guys, what I'll do, I'll show you with one of the example. I can show you how to calculate the Hessian matrix and all, and after that we'll directly move to the practical. So guys, now let's understand about the Hessian matrix. How does it work and how it's helping us to perform the smart quantization. So this matrix we use in a GPTQ, as we already know about it. So here I mentioned couple of steps just to give you the glimpse that how this Hessian matrix works. Okay, how this covariance concept works. X dot X transpose. So we have one linear layer. I think we already know about it. I shown you the calculation in my previous slide, right? So X is belong to the input, W is belong to the weights, which is a full precision weight, and this weight only we are quantize. Now as of now I took a basic example, but in a real time we are performing quantization quantization of the transformer. Now in the transformer, guys, we'll have weights, right? So we'll have weights in the attention layer. In the attention layer you will get a weights, as well as in the neural network layer also you will get a weights. Okay, so whenever we're talking about the weights, so it's not only the simple linear layer, it could be the attention layer, it could be the huge neural network. As of now I'm just explaining you the concept, so that's why I took a basic linear layer of the neural network. So guys, here you can see this is my input, this is my input, this is my weights. Okay, and here we are doing, we are computing the output. So y is representing to the output. Let me erase the entire earlier written thing. So yeah, so here guys you can see what we have the x, this is my x, this is my weight, and here is my output. This y is representing to the output. Okay, now guys, if we want to visualize this neural network, so how it looks like, so we have 3 rows, 1 row, 2 row, 3rd row, right? And how many inputs we have? 1 input, 2 input. So I will draw 2 input node. It's going to be connected with 1 hidden node. This input will come to this one, and then we will be getting our output. Now how many rows we have? So rows wise, guys, as I told you, we have 3 rows. So let me draw the rows as well. So this is my first row. My first row will go, then my second row will go, then my third row will go into this neural network. So you can write the value also. We just have 2 columns. So 1, 2, this is 3, 4, and then 5, 6. So first this row will go, then this second row will go, and then the third row will go. Now here is my weight, so I can write the weight also. So 0.5 to minus 1.0. Okay, now guys, these weight only we have to quantize. We're gonna quantize these specific weights. Okay, 0.5 to minus 1.0. So as you can see, guys, this is my output. Now what we are doing, so this is my output, guys, this is my output with the original weight, this one. This is my output with the original weight. Now what we are doing, we are taking a set of the quantized weight. We will take a random quantized weight. Now suppose your quantized weight is you quantize weight W. Okay, so after quantizing, guys, you are getting this weight. It is just a random quantized weight which I am taking. So 0.5 is as it is, minus 1.0 I convert into the minus 0.5. Okay, now what we'll do, we'll again perform the we'll again get the output. So here is my y hat. So x w cap transpose. So after calculation, guys, what I'm getting this particular matrix. Now what I'll do, I'll calculate the error. So y minus y cap. Okay, so we are calculating our error. Now here is my error. Now you can see over here, error is very large. Quantize harm output badly. Now guys, see, I just took an example. That's it, guys, right? But in a real time, whenever this weight would be, see, for sure this weight, this quantized weight is also being assigned randomly. Okay, quantized weight is also being assigned randomly, but we have to understand the flow over here. So flow is what? First we'll calculate the y, then we'll calculate the y hat, which with my quantized weight. Then what I'll do, I'll check with the error, then I will calculate the Hessian matrix. Now see here the role of the Hessian matrix. So H x transpose x. Now x transpose will be this one and x would be this one. So we are going to be calculated, and here we are getting this particular value, 35, 44, 44, 56. Now what I will do, so I'm using this Hessian matrix to judge the sensitivity. That's it, guys, nothing else. So here is my W minus W hat, this is my error, and this is my H, okay, Hessian sensitivity. Now what we are doing, so here is my weight, okay, here is my quantized weight. Now I'm doing a square of it. Now after that, guys, what you are getting this 0.25. Now we are going to be multiply this value with the 56. Okay, so here you can see in the Hessian matrix we have this 35, 44, 44 and 56, right? So we are picking this particular value 56, and see now error due to this change along the second dimension. So see what we are doing, we are going to be multiply just 0.5 with the 56 and we are getting 14. So big impact. This weight is a sensitive. So GPTQ won't pick up 0.5 for the quantization of the weight. Why? Because this value is very huge. This value should be the minimum one. Okay, this value should be the minimum one. I hope you're getting. So what we are doing, what is our main aim? So the main aim is very, very simple. So first we are going to be calculate the y, then we are going to calculate the y head based on the quantized weight. Now we are checking with the Hessian value, we are taking an error, okay, and we are going to be multiply with the Hessian value, and then finally we are getting this particular value, the final value. Okay, now this value should near to 1, sorry, near to 0. Okay, if it is very huge, it is very large, we can say it is having a big impact, means the weight quantized weight is having a big impact in the error, and we are not going to be choose that. So GPTQ won't pick this minus 0.5. So likewise it is iterating. Okay, likewise it is iterating on the multiple random weights and try to pick up one best weight. So that's the entire idea of the GPTQ, guys, right? Now what we'll do, guys, we'll see the practical of the GPTQ, how we can perform the practical, and then we'll move to the new technique, that is AWQ. Now let's start with the practical of the GPTQ. So guys, here I created one end-to-end notebook for all of you, and for sure I'll provide you the link of this notebook in the description. From there itself you can download it. Now guys, this GPTQ was the research paper which was published in 2022. So here is the research paper. I'll provide the link of this research paper as well. So definitely you can go through with it, and at least you can read the abstract, introduction, and the conclusion part. Then guys, behalf on this research paper, because research was the idea, research paper was the theory. Behalf on the research paper, one a GitHub repository was created. So this is a GitHub repository, and inside this repository you will find out the complete you will find out the auto GPTQ implementation from complete scratch, right? Even though this repository is not in action right now, this repository is archive. So you will find out some other repository. I'll show you that as well. I'll highlight that particular repository also. So if you see guys, if you are going to be access a code from this repository, or if you are going to be download a package of this repository, let me show you the package as well. So this is a package, auto GPTQ. This is the latest version. Now if you will check with the release history, so the release history you will find out the complete detail. So 0.7.1 this package was released in 2024 itself. So it's been more than 1.5 years this repository was not updated, and even they are not releasing the latest package. So if you are going to be use this older package, then I would suggest you please use Python 3.11. If you are not going to use Python 3.11, in that case you won't be able to use this particular package. And in Colab the by default version is 3.12. So I think so in Colab you cannot use it directly. Maybe you will have to change the Python version over there, or else you will have to create a virtual environment in your local or wherever you are configuring your server. There you will have to configure your environment with 3.11, and then only you can use it. But guys, the good part of this repository, see, even though this repository was archived, it is not in the like action right now, but the new repository have been created. So what is the name of that new repository? The new repository name is the GPTQ model. So once you will click on this repository, this word, right? So this highlighted word, this hyperlink. So you will be directly redirecting to this GPTQ repository. This is the very latest repository. As you can see, the last commit was on 16 minutes ago, right? Like last commit was on 16 minutes ago. So you can think guys how latest it is. So they have released their PyPy package also. You will once you will click on this PyPy like this icon, right? So you will get the PyPy package also, this GPTQ model 4.2.5. Now you can check out with the release history. So when they have released the first version of it, so they released the first version in 2024 itself. Okay, I think last year 15th August 2024 itself. So it's almost around 1 year, but yes, this repository is being updated. So the last release was the 16 September 2025. So I think 7 to 8 days ago only they have released their latest version. Now we are going to use the same library GPTQ model. Okay, and we're going to use the latest version as well. Here you can see the Python supported version. So it is supporting all the version 3.12, 3.13. So whatever latest Python version is there right now, it is going to be used the same version. Okay, up to that, even 3.9, 3.10, 3.11. So after 3.9, it is using all the version. Okay. Now guys, let's do one thing. Let's try to take a let's try to take a look onto this particular page. So over here they have mentioned each and every detail. As you will go through with this particular page, you will find out like basically what all model they are supporting, okay, and what all platform they are supporting. Now apart from that, how to configure, how to download this particular package, then how to basically load the model, okay. Now after loading a model, how to run it over the server, so that particular command also they have given. Then here you can see how if you have your own model, then how to quantize that specific model, okay. Now how to enable b2 level b2 of quantization for the higher accuracy and all. So many more things they have given over here over this page. If you are new to this particular library, then I would suggest you please try to visit this particular page. Your most of the doubt will be clarified, and easily you can use the quantize model as well as you can quantize your own model as well, right? Now coming to the next part. So here guys, I would like to show you something from the Hugging Face. If you are aware about the quantization and if you are using quantize model, so for sure you will be aware about this repository. The repository is very famous. The name is the blog, okay, the blog. So inside this repository you will find out around 3863 model, and this all are the quantized models. So it's a GPTQ quantized one, it's GGUF, AWQ. We'll see the AWQ, how basically we can perform the activation aware quantization, okay. Then GGUF, how to convert any file into the GGUF format, right? We'll see from scratch. But guys, this repository, under this repository you will find out all the quantized model, okay, whether it's a AWQ, whether it is GGUF, whether it's GPTQ, right? So I already discussed all the differences and all everything guys. Even the GPTQ model we can convert into the GGUF. GPTQ is nothing, it's a way of quantization, and then model, final model we are saving as a saved tensor or as a binary format. Now that particular format easily we can convert in one specific binary format, that is called the GGUF, okay. So this repository is a quite famous one. If you want to be use this model or this quantized model, feel free to use from this the blog repository. As you can see, the followers is around 25,000 and it's doing a very amazing job. Now coming to the next part. So guys, if you will check with this GPTQ library, so the GPTQ library is also maintaining one repository over the Hugging Face. So here guys, if you will go and check with the page itself, either the GitHub page or this PyPy page, there itself you will find out one hyperlink. So Hugging Face model cloud. Now you just need to click on this hyperlink and automatically you will be redirecting to their GitHub repository. So the name of this repository is modelcloud.ai. So this is the name of the company, modelcloud.ai, and with the same name they have created a repository also. So and see, they have created a different collection. So this is the first, as of now I'm able to see only one collection, okay. So here you can see under this model cloud repository you will find out each and every model. So guys, this particular repository is being maintained by this community, okay. Whoever has created this GPTQ, whoever has created this GPTQ model repository, right? So let me again give you the summary. So the summary is this research paper was released in 2022. On behalf on this research paper, this Hugging Face repository was created, but this Hugging Face repository is not being maintained currently, okay. This repository is being scrapped. Now behalf on this particular repository, they have created this new repository GPTQ model, whoever was maintaining this entire ecosystem. So this repository is compatible with Hugging Face, okay, and you will find out their Hugging Face repository also. So over there itself they are going to be upload their all the models and all everything, right? Here you can see all the model under this particular repository, model cloud, which belong to this particular repository only. Now they have released their PyPy page also. So if you want to get a quick start, right, what if you don't know about this GPTQ repository, GPTQ model and all, right? So you can visit to this particular page. Under this page you will find out the complete quick start code and all everything. For sure you can copy it and paste it inside your collab or inside a local, and you can test your application, okay. You can test your application with the cloud with a quantized model, or else you can perform the quantization of your own LLM as well, okay. Okay, I think this thing is clear. Now let's do one thing guys, let's see the practical which I created. Now here is the differences between the auto GPTQ bits and bytes and GPTQ model, and guys after that I kept the complete practical. So let's go through with each and every step, and let's see guys how we can load the quantized model and then how we can perform the quantization. So guys, before executing the code, let's see the differences between this auto GPTQ bits and bytes and the GPTQ model. Auto GPTQ is a deprecated library. Bits and bytes is still in use, and it's a very important library. while we are doing fine tuning and all. So last one is the GPTQ model. As I told you that this is a replacement of the auto GPTQ library, and it's going to be a future. Okay. Because here you will find out so many quantized model and all, and for sure in the future people are going to be use it, like the block repository which was based on the GPTQ. Okay, there you will find out all the other quantized model and all, but yeah, GPTQ is also there with the previous and the earlier method. Okay, now this comparison have been done based on couple of points. So here I mentioned all the points: origin, quantized method, target, hardware support, integration, inference kernel, training support, flexibility, evaluation, easy to use, community support, strength, weakness and all, right? For sure you can read it out. So let's take a look onto it one by one. So here if we're talking about the auto GPTQ, so it was part of the Hugging Face ecosystem. Bits and Bytes is also part of the Hugging Face ecosystem. It was created by this person, right? GPTQ model, again, it is a part of the Hugging Face ecosystem, and you will find out with under this repository, all the model under this particular repository. Then quantized method, so they were using the GPTQ method, the actual GPTQ method which was there in the research paper. Then this Bits and Bytes is using the linear quantization, int 8, NF4, FP4, 8-bit optimizer. Okay, it's a linear quantization. It's a simpler quantization, okay, compared to this actual GPTQ, but it is a type of the GPTQ only. Okay, then this GPTQ model is using the GPTQ1, GPTQ B2. Okay, it's a updated improvement version on top of the GPTQ. Then triple Q, EORA, okay, and then GAR. So what is this triple Q? Triple Q is a quick quantization for transformer. Here I kept the full form of all the words. So EORA, so it is similar to the LoRa, but it's an advanced or the updated form of the LoRa. Okay, efficient online row-wise approximation. You can check out the research paper of it, EORA. Okay, and yes, you'll find out the complete detail of it. Compensation for the compressed LLM with the eigenSpace low rank approximation. You'll find out the GitHub repository also of this particular concept, EORA. Okay, and then guys, yes, we'll be able to find out this EORA technique also under the GPTQ model, inside the new library. Now support wise, it is supporting the GPUs, it is supporting the GPUs, but it is supporting the NVIDIA GPUs, AMD GPUs, Intel GPUs, as well as the Apple Silicon GPUs and the CPUs as well. So this is a bit more advanced one, the GPTQ model. Okay, hardware support, as I told you already. Integration wise, Hugging Face transformer, PyTorch optimization, and Hugging Face integration. Now here also you will find out the Hugging Face transformer integration, but along with the different other framework like VLLM, SGLang, okay, Optim, PAFT and all. It is compatible with all the other Hugging Face library. Then inferencing kernel. So under this all the different framework, okay, you will find out the inferencing kernel for the auto GPTQ. You can load the mod, you were able to load the model okay, under this different framework and all, and then you can perform the inferencing. So yes, you can see inferencing kernel here is also QBLAS based int 8 kernel. Here is a Marlin, X Llama, Torch, Fuse, Bits, Blast, right? So these are some inferencing kernel, some different framework. Under there you can directly load the model and you can perform the inferencing. Training support, no. Optimizer is state, and here's a partial, means you can perform, it is not completely training, okay, it is just the testing on top of the calibration data, that's it. But in the original library, we were not having any sort of a support. Flexibility, yes, focus on the GPTQ only. Now here is the training inferencing. Okay, now here is dynamic per layer configuration, adapter, GAR, evaluation, eval integration technique. So this is a little bit advanced one compared to the previous one. Here we were focusing the GPTQ, the mathematics which we have seen. Okay, and here apart from that particular mathematics, we can like connect with different adapter. We can connect with the GR technique. Okay, and we can get the per layer configuration and all dynamically. Now here you can see the evaluation. So no built-in evaluation. Now here also no built-in evaluation. Now here they have created a built-in evaluation, LM eval and eval plus. I'll show you this part. Now ease of use, so it is very easy. This is also very easy, like this is a little bit advanced, and it is easy to use because it is also a high level API. Then guys, the next one was the here you can see strength. Okay, community support. The huge community support was there. As I told you, whatever model was the quantized, right, using this particular technique, all the model you will find out under this particular repository. This is also very, very popular. Okay, the Q's community support you will find out. Now here, this is growing rapidly, but in couple of years, maybe in 1 or 2 years, you will find out lots of model was trained with this particular repository, okay, which was based on the advanced GPTQ model, okay, advanced GPTQ quantization. Now strength wise, easy. Okay, now here this is a simple. Now here is all-in-one production, means you can say this is simple and effective. This is like easy to use through the Hugging Face, but guys, this one all-in-one, everything you will find out under the one roof, and this is a production ready like system, okay, ecosystem or the framework. Weakness wise, limited to GPTQ only, NVIDIA only. Now here more complex and newer ecosystem, and this is still is maturing. So this was the differences, guys. I hope this differences is clear. You can explore more about from your end. And now guys, what we'll do, we'll see the practical, okay, how we can install the package and how we can quantize the model, how we can load the pre-quantized model and all. And I was facing one issue, I'll discuss about that as well. And yeah, let's see, let's start then. Now first guys, you have to install the GPTQ package. So here is a command for installing the GPTQ package. Pip install -v GPT model -- no build isolation. So -v means what? Verbose. Okay, so while installing the package, you will get all the details over the screen itself. No build isolation means what? So pip is not going to be install the other respective dependency. Okay, it is only installing this GPTQ. Here I written the complete detail. You can read from your end. Now let me install it. So here guys, I'm going to install. Okay, now after this one, I'm going to update the protobuf package because earlier I was getting one issue because of this protobuf. So I need to install this basically below version, right? It should not be the latest version. It should be below to the 6.30. Now after installing this particular package, the GPTQ model, you will have to restart your session. So let it install, then we'll start the session. Okay, so I got an option to restart the session. So let me click on it. And yes, restart is done. Now let me install this protobuf also. So after installing the protobuf as well, you will have to restart the session. It will automatically give you the pop-up. So let it complete, then we'll restart. Okay, so this is also done. Now you can import this GPTQ. You can check whether you are able to import it or not. So once you will write from GPTQ model, import GPTQ model, you will be able to import it. Now what you can do, you can check all the folders, whatever is there inside this particular package, because this is what, this is just this GPTQ, import GPTQ, just it is this particular library, okay, this particular code which we are installing, which we are importing in the form of package. Okay, now here we are able to import it, and after importing it, guys, I can check all the directory, all the like packages, all the directory, all the folder inside this particular package. Okay, now after this one, see here I given you the link as well of this particular GitHub. So of this Hugging Face, you can go and check simply over here. You can check all the version under this model cloud repository, which I already shown you. Now after this one, guys, what we'll do, we'll load the model. So this is pre-quantized model. As of now, we haven't done the quantization from our end. We are going to be load the pre-quantized model over here. So let me load this particular model, the GPTQ model. Okay, so the name of the GPTQ model is llama 3.2 1B instruct GPTQ model 4-bit Vortex 2.5. Okay, so this is a quantized model which already someone has done, and we are just going to be loaded. Okay, so let it load, let it install in our system, and then I'll show you how to do the inferencing. And memory wise, evaluation wise, everything I will discuss in this particular video itself, so no need to worry. And guys, here you need to configure your Hugging Face ID as well. So don't forget to configure the Hugging Face HF token, Hugging Face token, and you know how to generate it. If you don't know about it, you can check out with my previous Hugging Face tutorial. There I already discussed how to take this token and how to keep the read token, write token, and all everything. So let it complete, guys. After that, I'll show you the inferencing part. Okay, so now this is completed, and what I'm doing here, I'm calling this model.generate, and I'm passing one command, I'm passing one prompt here. Uncovering deep insight begins with. Okay, so this is the half sentence. Now I will give this particular sentence to my model, and let's see what model is going to be generate. So this is a generative model, text generation model. So here it has generated the data. It has generated data in the form of IDs. So that IDs I'm going to be decode over here, so that I will get the response. Okay, so this is my response, guys, as you can see. So let me put it over here. So uncovering deep insight begin with a deep understanding of the underlying principle and the concept that govern the behavior of the system in question. So we are able to generate something with this particular model, and we can try out with some other good model as well, where we can directly use those particular model in a full-fledged systems, full-fledged conversational system, generation system, in summarization, wherever, in whatever way we are going to use the LLM. For those use cases, we can use this quantized model. Okay, this is just for the testing. Now guys, what I'm doing here, so here I'm going to perform the quantization on top of my own model. Okay, so I load the model, the raw model. Okay, I will load the raw LLM model, and on top of it I will perform the quantization. Okay, so let's see how we can do it. So for quantization of our own model, first we require the LLM model. So here is my model. My model name is llama 3.21b instruct. I'm loading it from my meta llama repository. We have other model also. You can definitely check out what model you can use from here, and you can load from the other repository as well. But the thing is, this should not be a quantized model. Okay, this is a raw model, raw LLM model. Then guys, I'm creating one more variable. The variable name is quant path. So under this particular folder, my quantized model would be available. Then here I'm loading my data. So this is the calibration data. On top of this particular data, my model tried to perform the mock training, not the complete training, because it already trained model. Now it will perform the mock training. It's try to find out the error, quantize error and all, and behalf on that it try to suggest the best possible quantized weight. I think you already have seen the mathematics like implementation derivation. So I won't think like you will face that much of issue to understand about the calibration data and all. Then here is the GPTQ model quantized configuration. I'm loading it from this particular package from the GPTQ model itself. Now here I'm defining this quantized configuration. Now under this I define two parameter. One is the bits and the second is the group size. So the meaning of the bits, in how many bits we want to be compress our model. Okay, so this model is having some sort of a weights. The weight would be with the higher precision, with the floating and all, floating values and all. Now if I want to compress it with the 4-bit quantization, so I will write that configuration over here. I will write that value over here. Then group size means how many basically weight, how many weights you can consider all together, right? In one single go, how many weights should be all together while you are quantizing the weight. Now here I'm loading my model, guys. So already I executed this particular line because it takes some time. If you are running it first time, it might take around 10 to 15 minutes. So see, already 6 minutes gone in my case. Now still it is loading a model. So guys, my model is getting loaded. So model is getting loaded. This is a normal and a raw model, and I'm loading it with the quantization configuration. Now after this one, what I'll do after this one, guys, I will perform the quantization. Okay, I'll call this model.quantize. I'll pass my calibration data, and I will pass my best size, right? Now one thing over here, guys, so once you will hover the mouse on top of this particular function, this configuration function, quantize configuration, you will get all the parameter inside this one, all the parameter of this class, right? So bits, dynamic, then the other parameter decrement, decrement activation, okay. Then damp auto increment, then damp percentage, then group size, then LM head, quant method. So you can see all this parameter, and it is having some by default value already. So where you will get the detail of all those parameters, so I already mentioned it over here. So let's look into some sort of a parameter. So bits is there. Bits means how many bits you want to be quantize your model. Okay, lower bit means more comparison, less accuracy. Dynamic means quantize some layer with 8-bit and other is skip the quantization. Now group size, 120 number of weights grouped together before quantization is smaller, better accuracy but slower, fast but larger will be the faster and the more compression. Now damp percentage, so 0.05 use in a Hessian damping. Damp auto increment, right? Damp descending act, okay, it was not a decrement, descending act. Now here is the activation group aware. So all the parameter, okay, so you can read the details and all everything. Now if you want to implement the improve version of this GPTQ quantization, you can enable this v2. Okay, once you enable this v2, you will get the GPTQ v2. Okay, this for the better accuracy and for the more BRAM required. So I mentioned the detail of each and every parameter. For sure you can go over here and you can read it out and you can mention inside the configuration itself. Now guys, see, my model is loaded. Okay, my raw model is loaded with this particular configuration. Now I have to perform the quantization. Okay, so GPTQ model, GPTQ model dot load. I loaded the raw model with I provided this particular quantize configuration. Now I got my model in this variable. Now what I'm doing guys, here I'm calling this model.quantize. Now see guys, once I'll call this model.quantize, I might get I might get memory issue, because in my free tier I have limited memory. So in that case, if I'm getting memory issue, I will not be able to complete this particular quantization process. Okay, see, I tried 3 times and all 3 times I'm getting memory issue. Now what I can do, it is suggesting me something. It is saying increase the best size to match your GPU RAM, GPU or the BRAM specification. Let's do one thing. Let's take 100 over here and let's try it one more time. Okay, I tried with the different values, so still it was giving me the issue, but I thought, okay, I cannot complete with the free tier of this collab. I think I will have to purchase the advanced version of it, Google Collab Pro, then only I can complete it. Let me take the another version. Let me take 500 over here and let's see whether we'll be able to quantize or not. So guys, still it is giving me the memory issue. Here you can see I'm not able to perform the quantization with this much of memory, because it is memory intensive technique with respect to the LLM based model, transform based model. So not an issue guys, you can try it out from your end. You can purchase a Google Colab Pro and there you can check. Otherwise in the next tutorial, what I'll do, I will create a dedicated tutorial on top of it. I'll take a Google Colab Pro variant version, okay, that I will purchase, and there itself I will perform the training and all everything, okay, of it. The quantized training, this is not an actual training, this is a quantization. We are going to be convert our weight from higher precision to lower precision, and for that we required some calibration data and all, just to mock the training, not the actual training. Okay, now guys, here what I can do after like quantization, my next step will be the saving the model. I can save the model, so I will give my path, and there in that particular folder my model will be available. Then after that, if I want to push this particular model, I can simply push it, use the Hugging Face. So here is my Hugging Face login. I can check whether my credential is correct or not. Then after this one, I can push this particular model to the exact repository. Okay, so this is the exact repository, and I'm from here I'm pushing the model, and here is my commit message. Now I can load the model, I can generate some sort of a like result from there. I can perform the inferencing, okay, on top of my own model. So this is a complete pipeline guys. If you are able to perform this quantization without any memory issue, then for sure you can run the further step as well. Means you can push your model to the Hugging Face, as well as you can test in your local. So guys, this was the practical this was the practical tip for the GPTQ model with this GPTQ model library. For sure you can go and check with this particular library again, and you will get more and more detail. Now let me explain a couple of more things. So guys, let's say if you want to evaluate the model, the normal model and the quantized model. So for that I written this particular code. So once you will get the quantized model, then definitely you can check it out. So what we are doing over here, so we have one method. The method name is what? Calculate average perplexity. It is taking model tokenizer text, okay, max length, best size. Now it's going to be calculate the perplexity. Perplexity is nothing, it is a score which we use for checking the quality of the generation. Now after calculating it, is going to be written the result over here. So here we are loading the normal model, here we are loading the quantized model. Okay, now this is my main function which is doing everything. So here is my model ID guys, here is my quantized model path. Okay, if we haven't performed, okay, so here it will check. So this is my calibration data, right? Now after that, what I'm doing, I'm going to be load the device, the exact device. So here I'm going to be set the device quantize. I'm loading the quantized model. Now here I'm loading the normalized model. If quantized model does not exist, then I will first train the first I will convert my normal weight into the quantized model. then only I will be getting my quantized model. If it does not exist already, then it will perform this step as well. I written in the logic, it can follow this one. Then I'm evaluating the model. So first I'm passing this normal model, okay, and I'm checking the accuracy, okay, I'm checking the score, the generation score, the perplexity score, then I'm checking with respect to the quantized model. So guys, likewise you can evaluate your model on top of this particular data, sorry, on with respect to this perplexity score, right? And you will be able to understand which model is good. Now accuracy, this memory wise also I written some code, so you can check like how much memory is going to be consumed by the normal model as well as this normal model as well as this quant model. Okay, so please check with this particular code, you will get the complete detail. Now what all memory details you will get from this code, let me highlight that also. uh, so this you will get the allocate memory detail, how much memory currently in use, okay, you will get it from both model, model 1 and model 2. I written a code in such a way that you can check with both model. Reserved memory currently hold by the PyTorch, okay, in use as well as the cache. Peak allocation highest ever use, and peak reserve highest ever hold by the cache. Okay, so this entire detail you will get with this particular code. Let me show you how you can check it out. Now once you will get your quantized model, for sure you can get a details. Okay, so let me scroll down and see this, all the memories being printed. So first you can check with respect to your normal model, and then you can check with respect to your quantization model. That's it guys. So right now we have a llama model. So what I can do, I can like check how much memory is being used. So let me do one thing, let me remove it and let me execute it. So it is saying syntax error. Now I can execute again. Load memory, load normal model is not defined. So load normal model, where is a load normal model? Here is this function, no? Correct. So let me take this particular function and let me keep it over here. So it will give me the normal model. And now let's try to check. So it is saying content configuration must be passed with instance content configuration. Okay, so here the quantization configuration should be passed. So where it is, I define it somewhere. Let me take that quantization configuration. Yes, this is the one. So I can take this quantization configuration and I can keep inside that one. So model, see, this is the quantization configuration, and I can keep it inside the variable, and now this particular variable I can keep it over here. Okay, now I think it is perfect, and you can see guys how much memory is being uses, okay, by this particular model. This is a normal one, it's not a it's not like a quantized model. Okay, after this one the quantization will, okay, so it is showing the out of memory. Guys, you can check it out. You can purchase the Collab Pro, or else I'll show you next time with the Collab Pro. Okay, sorry for that. I didn't check it earlier. I just like check it right now, and then after that I'm recording this video. Okay, so here you can see this GPT model is having one more library, LM eval, so it will give you the evaluation. So you can check with that also. So it also takes time. Let me show you what basically I evaluated with that. So at the end you will get one matrix. Okay, inside that you will find out some different column. So you will find out task, version, filter, and short matrix, value, and std error. Okay, standard error. So let's see what all like what is the meaning of all this column. So here you can see AWC means what? Accuracy. So and SDD means what? Standard error. Okay, so these are the evaluation metrics for the quantization model on the ARC challenge task. So there was one task like internally it is evaluating. So once you will call this model now, this once you will load this model ID, and you will call it this eval method. Okay, using the GPT model dot eval, you will give the model ID, and here is a framework. Okay, you will pass the framework, and you will pass the name. Okay, name on the evaluation, on top of which data set or which task you are going to evaluate your model. So it will load the model, and while it is loading this quantized model, it will evaluate that. Okay, so regarding that you will get the accuracy. Okay, it's a normalized accuracy, which is 0.27, means 27% accuracy, with the standard error 0.013. Okay, it's a statistical value. Based on behalf on this one, you can evaluate your model. Okay, the quantize model. Now I think this is clear. Now we have another way also to load the GPTQ model. The one is the bits and bytes. So in future we'll talk about it. So it is loading in a linear transformation. It is also loading the GPTQ based model only. So we have this bits and bytes configuration. So in how many bits we want to be load? Let's say in 4-bit we want to be load. So whenever we are going to be loaded from the Hugging Face, we just need to mention this configuration. Okay. So already we discussed while I was showing the comparison, and with using this one, we are not going to be load the exact 4-bit GPTQ, but yeah, it's a linear transformation on top of the original GPTQ itself. Okay, so this is also one of the way to load the GPTQ model with the lower configuration of uh, with the quantized model. Okay, the quantized version of the model. Now here we have one more. So XLlama is also there. So XLlama is a PyTorch C++ based CUDA implementation tailored for the llama model, working specifically with 4-bit GPTQ weights. So guys, this is also one of the framework you can try out. This framework mainly built with the C++, similar to the GGML, okay, similar to the llama.cpp, and this is specifically built for the llama model, llama style model. Now guys, you can utilize this particular framework, and using that also you can load the model in a 4-bit quantized format. Okay, and you can use those model and all. So whatever model you have, you can first download that particular model, or you can load it from the Hugging Face, and then you can pass the path to this particular class, okay, to this X llama v2 generator class, and you will be able to get your quantized model. So this was some another way to quantize the model in GPTQ format, bits and bytes. For sure we're gonna see in future. I can show you one full-fledged example on top of this as well, until you can try with this much of detail. Okay, it will also take some memory, so that's why I'm not showing right now, because my memory is already full. Once I will purchase the Google Colab Pro, at that time I can show you. Yes guys, so I hope so you understood about the GPTQ in a full-fledged manner, from mathematics to introduction to practical. Now let's see some other format like AWQ, QAT, as well as the GGML and GUF. Okay, so guys, let's start with the AWQ. So AWQ is a activation aware weight quantization. So in the name itself, you can see they're trying to highlight something. Activation aware weight quantization means what? So here in this particular quantization, now we are going to consider the activation value as well. Now what does it mean? I'll talk about that. I'll explain you with the example. So first let's see where this activation function lies. So guys, if you know about the neural network, so let me design one basic neural network. So this is my input layer. Now here is my hidden layer, and now here is my output layer. Okay, so this neurons are connected to each other. Now here is what? Here is my output layer, this one. Okay, now how the input will flow? So input, let's say input is my X. Let's say here is my X1, this is my X2, then this is my X3. Let's discuss with respect to this particular neuron. So here what I'll do, guys, I'll pass my weight. So weight 1, then weight 2, then here is my weight 3. Now how the calculation will happen? So the calculation will happen like this. X1 is going to multiply with W1, X2 is going to multiply with W2, and X3 is going to be multiply with W3. Okay, so let's denote this particular value with the Y. So this is what? This is my Y. Okay, now guys, what I'll do, so this particular value, this Y, I'll pass to the activation function. So here I would be having the activation function. Now this particular function, the activation function, we use for getting the non-linear output. So this particular equation is a linear equation. So if we want to capture the non-linearity in the data, so for capturing that non-linearity, we use the activation function. So we have different type of activation function. The most famous and the most common are the sigmoid. Okay, 10H is one of them. Then we have ReLU. Okay, and the different variants of the ReLU. ReLU is one of the best and the one of the very useful function. And then we have another variants of the ReLU. So we use these particular function, the activation function, okay, with respect to any sort of a node, right? Now, if we're talking about the weight, see, so these are my weights, W1, W2, W3. So we are going to quantize these weights in a GPTQ. But if we're talking about the AWQ, so there, along with this weight, okay, we are focusing on the output of this activation function as well. Making sense? I hope you are getting my point, what I'm trying to say. So let's see the further point. So here what I written, instead of blindly quantize weights, AWQ checks how each weights affect the output after going through the activation function like GELU and ReLU. GELU is nothing, it is a variant, of the ReLU only. Then prunes and rescale weights so that they can cause minimum distortion in the output. So the moral of the story is very simple. Here what we are trying to do, we are trying to quantize the activation value as well along with the weights. Okay, so let's see the differences between the GPTQ and the AWQ. This differences I'm concluding and I'm doing based on couple of points as you can see over here. So guys, first point is the error handling, error modeling. The second is the use Hessian, calibration needed, whether calibration data is required or not in AWQ, precision, speed, accuracy, quantization target, and the use cases. So let's see the GPTQ first. So GPTQ, yes, we are taking the error, yes or no. Yes, weight only error. So we are going to be we are after the quantization we are going to check the weight error. Okay, how much error is there between the normal weight and the quantized weight. I think I already shown you the derivation and all. Use Hessian, yes, we're going to use it here. Calibration data, yes, we're going to use the calibration data here. Now if you will check with the AWQ, so this AWQ also is a post-training quantization. It is also post-training quantization, guys. Okay, don't think guys this is like a quantize aware training. No, it belongs to the post training quantization only. So you can say it's the updated version or the variant of the GPTQ, and this particular concept have been identified above the GPTQ itself. I'll show you the research paper and all, library, practical implementation, everything guys, don't worry. Now Hessian wise, yes, we use the Hessian and we don't use Hessian over here. Hessian means what? Hessian means it's a second order gradient. It's a gradient of gradient. Okay, second order gradient. So if we are finding out a slope, right? If we are calculating a slope, then we are again differentiating that slope. Okay, so that's going to become a curvature. That's going to be capture the curvature. Okay, instead of the slope, see in the first derivation we are going to capture the slope, but in the guys in the Hessian we are going to looking into the curvature. Okay, now calibration needed, yes, calibration needed, yes, here also calibration needed. Now why this calibration is required? So that we can mock the training. Okay, we can mock the training, we can check with the quantized weight. Okay, we can differentiate between the quantized weight and the normal weight, okay, with respect to that particular data. Now precision wise it use the int4, it is also used the int4 commonly. Then speed wise it is fast, it is even faster. Accuracy high, very high, okay, compared to the GPTQ. Now quant target weight plus activation impact. That's it guys. Okay, use cases, all the LLM model, llama GPT, here also llama, mistral GPT, whatever LLM models are there. Now I kept couple of analogies. So real time analogy, GPTQ measures how much raw ingredients change. Okay, because see in the GPTQ what we are doing, in the GPTQ we are focusing on this weights, right? So let's say we have a matrix, the matrix is having this 1 2 3 4 5 6. Now this is my input x. Okay, now here I have a weight, so weight in the weight, let's say we have this 0.53, 0.45, 0.36, okay, then 0.32, 0.331, 0.565. So now what we are doing, we are going to perform this X W T. Okay, this is going to become my output. Why? So whenever we're talking about the GPTQ, we are only focusing on this particular value. That's it, guys. But guys, if we're talking about the AWQ, so along with this particular value, we are considering the output of the activation function as well. So this is my final output of the node. Okay, and this is what we are considering in the activation function. So we are considering the activation value as well as the normal weight. That's it. So I kept the entire practical and all everything, and even the mathematical intuition. I'll discuss those part. Now here AWQ means measure how the final dish test after the cooking. Okay, this is just a like analogy. I think this will make your understanding a little better. Now why this GPTQ is better than the why this AWQ is better than the GPTQ? So GPTQ focus on a pre-activation error, used some second order gradient, slower on a larger model, and good for the precision. Now we're talking about the AWQ, so focus on the post activation, the real output error, no gradient. Okay, means we are not going to calculate the second order gradient over here. Faster, there is no Hessian, right? So if there is no Hessian, means there is no derivation of derivation, then it is like little faster, better for both precision as well as the speed. So it could be the one of the choice on top of the GPTQ, right? I hope guys you like this introduction. Now let's see some mathematical points, mathematical intuition, and then we'll come to the practical, guys. Okay, so guys, let's see the mathematical intuition of the AWQ. Here I'm not going to show you the complete derivation. I'll just give you the glimpse of all the steps, because I already shown you in the GPTQ. A couple of points is different over here, but yeah, with this high level overview, I think so you will be getting that. The complete derivation is not required. Now, before coming to this high level overview of the mathematical intuition, let me show you the research paper of the AWQ. Now, once you will search AWQ research paper over the Google, you will get the link. You can simply check out with this archive. Again, now you can see this paper was released in 23 itself, so submitted on 1st of June 23, and then last revised on 18th July 24 itself. Okay, now if you want to get the PDF version of it, so simply you can click on it, view PDF, you will get the PDF. Now here inside this research paper, you will get that they are trying to reduce the weight of the LLM model, the large language model. Okay, this paper is quite amazing. Behalf on this paper, you will find out one GitHub repo as well. I'll show you that. Now here inside this paper, they have mentioned each and every step. Okay, how did they perform the quantization? What was the benchmark result and all everything? Okay, and apart from that, how the model was behaving with respect to the different metrics and all, right? Every sort of a thing you will get inside this research paper, and apart from that, you will get about the evaluation. So which framework they were using for running this particular model and all, right? Every sort of a detail you will get over here. So at least try to read the abstraction, introduction, conclusion, and try to read it on a high level, so that you will get some like the real detail of this AWQ, instead of going through with chat GPT or any like blog or something. So first try to read from the research paper, or and then basically you can revise the entire concept and all from the chat GPT, or basically then go ahead with any blog and all. Now here guys, with respect to this particular research paper, you will find out one GitHub also. So this the name of the GitHub is Auto AWQ. So the research paper name was the Auto AWQ. Okay, activation aware weight quantization for LLM comparison and acceleration. Now behalf on this particular research paper, they have released this GitHub. Now you can see the disclaimer here. The disclaimer is this repository was archived by the owner on May 11th. Okay, so this repository not in use. Why? Let me show you the reason behind that. So just try to read this entire detail. What they are saying, it is not secret that maintaining a project such as AWQ that has 2 million downloads, 7,000 plus models on Hugging Face, and 2.1k star is hard for a solo developer who is doing this there in a free time, right? Important notice. So AWQ is officially deprecated and will no longer be maintained. The last tested configure was on Torch and Transformer on top of this version. So if you want to run this particular package, you will have to use this specific version. Otherwise, it will show you the error. Now, in future version of the transformer break auto AWQ compatibility, please report the issue of the transformer project. Means if you want to be use the project, this auto GPTQ, in that case, you will have to use this particular version. If still you are getting error, then you will have to report to the transformer itself. And now, alternatively, okay, read out to this thing. This is very much important. Auto AWQ has been adopted by the BLLM project. So now guys, whatever functionality was there under this particular repository, now you will find out that particular functionality from the VLLM. Now VLLM is having one specific module. The module name itself is called the LLM compressor. So under this LLM compressor, actually you will find out this particular repository, and with a single line of code, you can perform the AWQ quantization with respect to your own model. Okay, so that was a complete highlight with respect to this repository, and this was very much important because you might get confused. Now you will find out several other repository. So there is one more famous repository, LLM AWQ. For sure you can go ahead with this repository. They have shown that how to use it. You just need to create a virtual environment after cloning this repository, then install setup.py. After installing it, what you have to do, you have to run this particular commands, and with this single command, this particular command, you can quantize your model AWQ. You can perform the AWQ quantization with respect to your own model, right? So I hope guys this entire thing is clear. Now you can explore more. So this is this link will redirect to you on top of this repository, okay, which I shown you recently, LLM AWQ. This was on top of the actual research paper, okay, the initial repository, but now it is replicated, it's owned by someone else. Now apart from this one, you will find out AWQ over the Hugging Face as well. So here they have shown all the they have shown like how you can load the AWQ based model. So there are so many model AWQ based model. Now here you can see the model list. There is almost 8,000 model, okay, in each and every repository, in different repository, you will find out the AWQ quantized model, okay. For sure you can check out with any of them, and you can use accordingly. You can check this DeepSeek based model, Quen model, right? You can check out with some llama model, okay. There are so many DeepSeek based model which was quantized in AWQ, or else if you want to find out a AWQ quantized model, you can check out with the blog repository, okay. So inside the blog repository also you will find out so many AWQ quantized model, right? So you can directly use from here itself. So guys, let me summarize all the things. So this was a research paper. Behalf on this repository was created, okay. Now this is not going to be maintained further, it's going to be maintained by someone else. That the module name is a LLM compressor. There is one more repository which you can use for perform the quantization of your LLM model, okay. And apart from this one, if you will directly search over the GitHub, you will find out so many model, AWQ model, okay. There is more than 8,000 model. Now if directly you want to be check what all model we have, right? So you can look into the blog repository. It's having all the AWQ quantized model, okay. Now let's see guys, let's see couple of points, okay. The high level mathematical intuition, and then I will come to the practical guys. So for the practical guys, again I created one notebook. So before coming to that LLM compressor, the latest library, I would like to show you the previous library, okay. The previous library name was the auto AWQ. Just now we have seen that. So here guys, what I'm doing, I'm going to be install the auto AWQ along with the transformer and the accelerate. Now guys, here if you are going to be use the latest version of the transformer and the PyTorch, in that case it won't work. So what kind of error you might get, I'll show you that, okay. So here I'm going to install the AWQ along with the transformer, the latest transformer and the accelerate, and I'm going to use the latest version of the PyTorch as well. So for sure this auto AWQ is not going to work because they are not going to be updated anymore. Now after installing it, what you will do, so you will import torch, you will import auto tokenizer, auto config, GC, and then you will import this OS. Okay. Now here this GC is nothing, it's a garbage collector. So whatever cache memory and all extra memory you have, you unnecessary memory, it can vanish that. Now after that guys, what you will do, you will import the auto AWQ for causal LLM. So using this particular class only, you are going to be import the model, and then you're going to perform the quantization on top of it. So here is my model guys, this is my model ID, and I'm going to be load the tokenizer of this particular model. This is just for the validation, okay, whether the CUDA is enabled or not. Then after that guys, what I'm doing here, so here I'm going to load the tokenizer. Okay, so loading the tokenizer, so auto tokenizer from model base model, and then this is my tokenizer. Inside this particular variable I'll get my tokenizer. Okay, I hope you got it. So I think this is the redundant step. I can remove this particular step, I can comment it out so that you will not also follow this particular step. Then guys, after loading the tokenizer, we have to load the model. So auto AWQ for causal LLM, we have to load the model. So we are giving the base model name. This is not a quantized model. Now the quantization will perform after this one. So here is my base model. Then this is the other configuration: low CPU memory uses, yes, restore, use cache memory, false, trust remote code, yes, this is true, torch data type. So we are loading it with this particular precision, device map. Okay, so whether it's a GPU or CPU, we are going to be load with this particular configuration. Now after that guys, we are going to set it as a model. We are going to set to the evaluation mode. Then here is my quant configuration. Okay, so 0.2 coin group size, how many weights you are going to be considered in single go, or in which bit you want to be quantized. In 4-bit I want to be quantized, version GEMM. Okay, so it's a version of the like AWQ, right? You can check the entire detail and all everything. So this is my data, the calibration data guys. So on this particular data my mock training will start. Okay, then guys here you can see what I am doing. So it's my configuration. Okay, I'm going to be keep inside this particular variable. This is my calibration data. I'm just refine the data, and then here is my model.quantization. Now once what I'll do guys, once I'll call this model.quantization, my training would be started. And here you can see, so after the training what we can do, we can save inside the specific directory. Now guys, I was not able to perform the quantization. Why? Because the library was not matching. I was getting so many errors over here, and this errors are pretty obvious. Why it is pretty obvious? Why basically it is expected? Because this is not this like library is not the up to date, right? It's not going to be matched with the current version of the PyTorch as well as the transformer. So guys, now let me show you the latest implementation of this AWQ. So I will give you this particular notebook as well. You can analyze it, and you can run it with the previous version. So if you want to check the previous version, then what you can do, you can go through with this particular GitHub, the auto AWQ GitHub, and there once you will scroll down, you will get the version of the PyTorch and the transformer. Okay, if you want to check the transformer version right now, you can simply check with the pip show command. I can show you that which version I'm using currently. So give me a moment. I'm just checking over here. I'm writing pip show. Okay, transformer. So guys, maybe I'm using let me see, let me check. Even I'm not able to get which version I'm using currently. So it is 4.561, and what version they are suggesting to us? 4.51. Okay, so yeah, the difference is like too much here. 4.51 to 4.56. So please use the recommended version and try it again. You can quantize with the previous way in the with the previous the code itself. Okay, the previous model itself or the library itself. Okay, now let's see the LLM quantization with the VLLM. So what you have to do here, you just have to install this. You just have to install this particular package, the LLM compressor package. After installing this LLM compressor package, you have to load this AWQ modifier and this method, one shot method. Guys, you won't believe this one shot method is doing everything for you. Okay. Now here you will write in the AW modifier, you will write the schema name W4A16. You can read out the complete detail and all everything. Once you will hover the mouse, guys, let me disconnect from here. So disconnect and delete the runtime, yes, and now I can connect it over here. So you will get the entire detail on everything once you will hover the mouse over here. So AWQ modifier, it will give you several parameters: schema, target, ignore. So what you want to ignore, okay, in the what you want to ignore in the basic attention layer. Okay, now in the attention layer in the transformer block, right, attention plus neural network. Now here the target wise it is linear, okay, it's non-linear, so you can mention over here. Scheme wise, I think we'll have to check what is this. I think it is replicated to the version, okay, version of this auto GPT, sorry, AWQ. Then guys, after cooking this recipe, right, so I kept the name as a recipe. In the official documentation, the name was the same recipe. So here I am writing a model, here I am writing a data set. Okay, this is for the calibration data. Here I am giving the recipe, here I am giving the output directory. After the quantization, I'll get my model in this directory. Max sequence length is this much, number of calibration sample is 512. So once you will provide everything to this particular method, you will be able to quantize a model. You will be getting your quantized model, but the thing is here, I was getting the out of memory error. Everything was going smoothly, but suddenly I was getting out of memory error because I'm onto the free variant of the collab, and there I don't have that much memory, so I can basically perform the AWQ quantization with respect to this model with this much of data. I think I will have to do some hyperparameter tuning over here. Means we'll have to change the model name from this to some even the smallest model. Even this is the small model. Okay, it is 8B model. I can check with a 1B of model. Okay, with 1 billion parameter, I can take even the smaller sample. So this thing I'm leaving on to you guys. I shown you the entire thing. Now it's your time. Okay, now what you have to do, guys, you have to use this particular notebook LLM AWQ with VLLM. Do everything whatever I have done, okay, and explore a bit about this AWQ modifier. It here only you will get the complete configuration, and then try out with the smaller model as well as the small data over here. That's it, guys. So yeah, now let's see the next type of the quantization, which is QAT. That is also called the Quantize-Aware Training. So let's start with that now. Now guys, let's discuss about the Quantization-Aware Training. So already we discussed about this Quantization-Aware Training in the previous video. But now let's discuss with respect to the large language model. In large language model, we have lots of parameter compared to the normal artificial neural network or CNN model. If we are going to consider the huge CNN model, in that case also we would be having the millions of parameter only, but LLM is way more huge than those CNN model. In LLM we will be getting billions of parameter, right? So let's see how we can perform this quantization aware training using the LLM. So guys, let's discuss one by one. Let's discuss each and every point here. So summary, what is a summary? Simulate quantization during training. So model learns how to handle lower precision. So guys, this particular concept I discussed in my previous video also, that in the QAT, we are going to simulate the quantization, simulating the quantization. Simulating the quantization means what? So that is not this is not an actual quantization. Okay, we are simulating in lower precision, so that, okay, so that model can learn how to behave in the lower precision. Okay, maybe this thing will not be clear in a single shot. For that, what you can do, you can check out with my previous video. There I already discussed this QAT with one CNN model. Okay, there your understanding will be little more clear about the QAT, and then you can again rewatch this particular session. Now here, insert fake quantization and dequantization ops during the training. Back propagation will still be used float 32, but forward use simulation int 88. After training, you convert to the real int 8. Okay. So while I'm going to perform the training, okay, at that time I'm simulating the lower quantization. But guys, whenever we are going to be convert, okay, after the training, whenever we are going to be convert our model into the full quantization, I'll be getting my exact int 8 weight. So how this thing will perform, we'll discuss it, don't worry. Now, what is step I need to follow if I'm going to perform the quantization using the QAT technique? QAT technique means quantize aware training. Okay, so at the time of the training itself, we are going to perform the quantization. So we need to decide what to quantize, right? If we're talking about the LLMs, so in the LLMs we would be having so many layers. Okay, we would be having embedding layer, as we know. We would be having the attention layer. Okay, we would be having the feed forward neural network layer. We would be having the norm layer. Okay, batch norm, uh, or layer norms. It's called the layer norm. So layer norm layer, normalization layer. So these many layer. Now in all these layer, we would be having weights. Okay, weights. Now what to quantize? So that's going to be our own mind. Okay, so we'll have to check what needs to be quantized while we are going to perform the quantize aware training. So guys, here I written a name. We can quantize the embedding layer. We can quantize the layer normalization. We can quantize the final head also. Okay, in the output, in that transformer, the final head is nothing. It's the output of the neural network. Now, usually we focus on these particular matrices. So matrix Q matrix, K matrix, V matrix, okay, O matrix, then up, gate, down. So these all are metrics, right? These all are matrices. Proj means what? Proj means projection. Okay, projection. So proj means what? Projection. So guys, we always focus on these matrices if we're talking about the LLM. Okay, LLM, and we're trying to quantize these particular value. Now, why quite expensive for the LLM? Okay, so let's understand that model size in LLMs we would be having billions of parameter. Okay, billions of parameter. Because of that, quite is an expensive one. You know guys, the training of the LLM, how much complicated it is. It is very resource intensive technique. Okay, it's very resource intensive task. Resource intensive task. Right now, think if we are going to train our LLM, our own LLM, will it be possible? No. Let's say we are able to train our model, if we are able to train our LLM model, in that case, the higher computation power will be required. So maybe I have so many GPUs, okay, or I have very huge server, right? I have purchased very huge server with a with a very good GPU. Okay, so guys, uh training LLM is not a small thing, a small task. It's a very huge task, and computation will require a very huge. And because of that, this model size, okay, and model training, like it's not an easy thing. Okay, model size will be very very huge, and quite will not be possible. It's not. It won't be very very easy in that case. Now, fake quantization every forward pass. So in quite every forward pass applies fake quantization with rounding and clamping. Rounding means we are rounding the value. Let's say we have 27.01. So I'll just keep 27 over here. Now we're talking about the clamping. Clamping means what? It's a range. So in which range I want to convert my data. Let's say from 128 to I want to convert into the 127, or it could be 0 to 255. Okay. So it could be 0 to 255. So this could be the range, right? One of the range over here. Now backpropagation cost, guys. So backpropagation, even with a fake quantization, gradient are also completed in FP32. Okay, so there mean no memory, no VRAM, and definitely we are going to be struggle. Okay, with the memory itself. Retrain requirement in PTQ, the model is quantized without retraining. We all know, right? We're talking about the PTQ. In that case, we don't require the retraining, right? We don't require the retraining. Now we're talking about, right? If we're talking about QAT, in that case, guys, the retraining, uh training, actually training will be required. because at the time of the training only, uh, we are going to simulate the quantization. Now, resource requirement, yes, I already told you what kind of GPU would be required. So I mentioned a name, 4 to 8 GPU at least with 80 GB. Okay, 80 GB VRAM, 4 to 8 800 80 GB GPUs. So this 80 GB is representing to the VRAM. Now, QAT on Llama 65 billion. So dozen of GPUs on an industrial scale. If you want to perform the quantization of the llama model, quit of the llama from scratch. That's why big labs, Meta, Microsoft, OpenAI can afford it, but it's too expensive and individual. I'll talk about the different research paper on the quat. Okay, but I think so now you got the clear cut idea. So what is the alternative? Here I mentioned the alternative also, PTQ. So PTQ means GPTQ, AWQ. Already we have learned about it. LoRa plus QAT. So it is also called the partial QAT. Okay, this is also very famous technique if we want to perform the quantize-aware training. Then guys, we have a hybrid approach. So keep embedding in F32 and quantize linear in the attention layer to the int 8 and int 4. So this also could be one of the technique, but here we'll have to keep this embedding in FP32, and then rest of the layer we can convert into some rest of the layer. Basically what we can do, we can quantize. Okay, we can perform the quantization of those particular layers. I hope this entire thing is clear. This theory was very easy. Now let's see practical. Now see some let's see some research paper in all. Okay, and then we'll go with the final one, which is GGML and the GGUF. Now guys, let's start with the practical. So before starting with the practical, I would like to show you a couple of research papers so your understanding with respect to this quet will be bit more clear. So here is the first research paper guys, which was published in 2016. Yes, so this quet is not a new topic. This quet is a quite older topic. As you can see in the 2016 itself, the research paper was published with the name of quantized neural network training, training neural network with low precision weights and activation. Okay, so people are practicing all this thing since a long time, but now this LLM and all, it's booming a lot in the industry, and no one is using those classical model like ANN model or any machine learning based model and all. So that's why guys, we all have to move into the LLMs, large language model, and I will show you the latest research with respect to the large language model. Okay, now here guys, in 2016 itself, the first research paper was published. Maybe before that also a couple of research paper was published. I haven't checked with the Google and all. Okay, I haven't performed that research, but yeah, you can check that out. Now the second very popular research paper was published in 2017 itself, right after this paper. Okay, right after this training neural network with lower precision weights and activation. So the research paper name was the quantization and training of neural network for efficient integer arithmetic only inference. Okay, so quantization and training means what? So the time of the training we were performing the quantization for what? For efficient integer management, right? So it's all about the quantization only, and at the time of the training. So guys, this two research paper was very popular. Okay, you can go and check out the PDF, and at least you can read the abstraction and the introduction of these particular research paper. So this research paper from the Google end, and let's see. I think this research paper also from the Google end itself. I think nowhere has mentioned the Google. Okay, this is not from the Google. So the technology. Okay, I think from the Israel Institute of the Technology. Okay, so Columbia University, then again Institute of the Technology, and then University the Montreal, Canada. So guys, I think this was the joint venture. Okay, joint research from the multiple universities and the multiple basically colleges and all, right? But guys, this was published from the Google's end, this particular research paper. Now we're gonna see the final research paper on which the current LLM quantization, the aware quantization aware training is being performed. So that particular research paper was published by the Meta. Okay, what was the name of it? So the name is LLM Quant Data Free Quantization Aware Training for the Large Language Model. Okay, so data free quantization aware training for the large language model, and when it was published, so it was published in 2023. Okay, so 29th of May 2023. And if you would like to see the complete PDF and also, please click on this particular link, this hyperlink. Now after that you will be directly redirected to this PDF, and here you can see the complete detail of the researcher. So Jaquan Liu, Barles, Ogunj. Okay, then here you can see a couple of more names. So I think 2 Indians, okay, 3 Indians are also there. Yazhar Medat. Okay, I'm not sure about this guy, but yeah, this guy is an Indian. Raghuram, okay, Raghuraman Kishori, Krishnan Murthy, Vikas Chandra. Okay, so this all are from the Meta. So guys, this particular research paper, LLM Quantize-Aware Training, data-free Quantize-Aware Training for the large language model was published from the Meta itself, and this is very popular paper in the field of the quantize aware trading. You can read out the detail everything basically. So I just went through with this particular research paper. I just taken some high level knowledge from here, and I found it really really helpful. Okay, so guys, I hope so this thing is entirely clear now. If you want to take any quant model, okay, quantize aware training based model, so simply you can check out with a git with a basically Hugging Face. There you will get your quantize aware training model. So this one model I found from the Google itself. The model name is GMA. Okay, so GMA 34B IT quat model. So this is the quantize aware model. So this is all the checkpoint you will find out. Okay, you can check with the other model also. You can simply search into this model hub. Okay, you will be getting all the quat based model. So I can simply check over here quat QAT. So different quite based model I'll get over here. Okay, so as of now I'm just able to see the GMA itself, right? So quite is a heavy training, heavy computational thing, right? So no one, everyone can perform it. But guys, yeah, you can perform your quantize aware training with respect to any of your model, but you require lots of resources in that case. So let's see, let's look into the practical how we can perform the quantize aware training with one very basic model. The model name is going to be Distill GPT. Okay, so here I cap the entire code and all everything. So first of all guys, what I'm doing, I'm going to be import couple of its statements. So first is the torch, the second is the quantize. Okay, torch.quantize. I written the alias name over here, TQ. Then the third is a transformer. Okay, from here we are going to be import this auto import causal LLM and auto tokenizer. So here is my model name Distill GPT. From here I am going to be load the model as well as the tokenizer. Now here guys, I written the quite configuration. So activation, so this is for the activation, this fake quantization, and this is for the weight, this fake quantization. Okay, so observer, so this TQ, okay, torch quantization dot moving average min max observer is going to be my observer. Then quant minimum, quant maximum. So between these particular value I am going to perform the quantization. Now here you can see D type torch q int 8. Okay, so in this particular data type I am going to be convert my weights. Then q scheme, so here torch dot per tensor affine. So here we are going to perform on top of the tensor, not on top of the rows, right? Then here is a weight quantization. You can read the complete detail of it as well. Now here what I'm doing guys, I'm not going to be perform the quantization of the embedding layer. I'm going to be perform the quantization of the linear layer QKV. Okay, so that's why I'm keeping it false. Then what I'm doing here, I'm going to keep the entire configuration under this model configuration. Then here I set model as a for the training. Okay, then here my torch quantization dot prepare quat. Okay, I'll call this particular method and I'll keep my model in place is equal to true. So what is the meaning of it? Model now has fake quantization operations. So now my model is going to be quantized. Okay, while after setting this particular detail, now I'm going to be import the tokenizer. Okay, I'm going to be initialize the tokenizer. Now here is what, here's my label. Okay, now what I'll do, I'll call torch optim adam. So I'll be getting what, I'll be getting my optimizer. Now here is a complete training guys. Okay, so this is not a training from scratch. Okay, let me explain a couple of points guys. So let me explain you over the blackboard itself. I hope it is visible. So guys, if we're talking about the QAT, okay, so QAT means what? QAT means quantize aware training. Okay, quantize aware training. Now guys, tell me, if we're talking about a training, so can we perform this training from scratch? Is it possible to perform this training from scratch? If we're talking about with respect to this LLM, so this task is going to be very, very challenging, right? As we know. So this task is a very, very challenging with respect to the with respect to what? With respect to the LLM, right? So what we can do, so while we are training the model, while we training the LLM, okay, training the LLM, at that time only I can perform, at that time only I can perform this QAT, okay, or else guys what we can do, so after the training, okay, after the training, after the training, right, again I can perform the training of the model, so that is called the fine tuning. So the QAT process which I shown you, right? So I shown you at top of the fine tuning stage. Okay, fine tuning stage. I hope now it's getting clear. And here I just took very basic model. So my model was the distill bird, right? You can take any other model also. You can take you can check out with the llama at least. You can check out with the Mistral. Okay, you can check out with the DeepSeek. So these are some good and the huge model. You can check out with this particular model, and then uh, you let's observe that whether you are able to perform the QAT or not. Okay, I hope this entire thing is clear. Now coming to the next point. So guys, here you can see we have started the training. So we have a model. I will get my input and labels. Okay, that will be my output. We are going to be calculate the loss, backward training, then applying the optimizer, and here I am checking the and guys, here what I'm doing, I'm checking the loss at every 10th step. Okay, so likewise guys, what I'll be getting my loss, and after that, see, after performing this entire training with the fake quantization, with the fake activation and the weight value, I am going to be convert my quantized model into fully int 8 model. Okay, so this particular step will convert my model into the full int 8 model. Okay, so this is called the quantize aware training, guys. Please try to practice from your end and read as much as possible. I would suggest you please go through with the latest research paper and at least check the repository which was maintaining by the llama itself. So here you will find all the models, okay, inside this particular folder. Now apart from that guys, okay, so apart from that, what you will get this readme. Please read out this readme. Please understand how to set up this GitHub and all, and how you can directly use it. Otherwise, in whatever way I shown you with this PyTorch or PyTorch optimization, there's one more library, PyTorch optimization. You can check out with that also. There is also a couple of functionality with respect to this transformation. Sorry, this QAT, quantize aware training. Okay, yeah, this is it for this particular video, guys. Now let's see one thing. Let's look into the GGML and the GGUF also, and after that we'll guys conclude this particular video. Okay, GGF and GGML is also very important. Let's take a look onto it. Now guys, let's start with this GGML and the GGUF. So first we'll see the differences between this GGML and GGUF. I will cover each and every theoretical point, and then we'll come to the practical part. I'll show you the complete practical. Now before starting with this theory, let's look into the GitHub of the GGML. So GGML is one of the very important project. So here guys, once you will search this GGML org GitHub or GGML GitHub, you will directly get this particular link over the Google. You just need to click on that and you will be directly redirecting to this particular page. Okay. Now here you can see around 13.2k stars, 1.3k fork, and this library was very, very useful for running the LLMs, right guys? So this is C based library. This library is based on the C language. This was initially built on top of the C language. Yes, guys. And
using this particular library, using this particular framework, or you can see using this particular inferencing engine, we were able to load the larger and the huge model even on the smaller device. Yes. So guys, the impact of this library was very huge. Now, behalf on this particular library, one more library was created, and now I think you will be shocked by seeing the name of that library. The library name is llama.cpp. Yes, guys. So this llama.cpp is nothing. It is an extension of the GGML. Okay. So GGML was written in the C language, and this llama cpp was written in C++. Now here you can see the number of folks and the number of stars. It is very huge because everyone is using this particular library on their server just to load the model, just to perform the inferencing. And even on the smaller device, on any chip, on any embedded system, on any mobile system, okay, we can configure this library and we can load the LLM models. Okay. So guys, this is the importance of this GGML library, and I think we should be aware about it. Now coming to one research paper. The research paper name is Mind the Gap: A Practical Attack on the GGUF Quantization. Now, what is a GGUF? Where it lies? Okay, so we know GGML. Now we know GGML is a library. It's an inferencing engine. We can load the quantized model or LLM model. But what is the GGUF? So guys, GGUF is nothing. It is just a file format. It is a binary file which is having some advantage on top of the normal binary file. Okay, I'll come to that. I'll show you that what all advantage it is having. So GGUF is a file which we can run inside the either in llama cpp or in GGML. Okay, generally we use it inside the llama cpp itself, and this was invented by the llama cpp guy only. Now let's look into some theoretical points. So the points which I capped over here, and I think now you will enjoy a lot this particular point. So step by step, one by one, let's discuss it within next 5 minutes. So guys, if we're talking about any HF model, so this HF model is a LLM model. Okay, LLM model. So what we are doing, guys, we are going to quantize this particular model. Okay, and after quantizing, so we can quantize in int 4, int 8, right? Then either so after quantizing, we are going to be converted into the GGUF. So GGUF is nothing, it's a special dot bin format. Okay, then we are loading it, or we are in running it, or we are inferencing it inside the llama cpp or GGML. So the normal bin file we were running inside the GGML, and we were having one special bin file that is called the GGUF that we are running inside the llama cpp. So llama cpp is nothing, it is an extension of the GGML library only. Now this quantize, guys, so we have HF model. So either we're gonna perform the quantization before loading into this llama cpp on GGML, or nowadays this llama cpp is having capability, it can perform the quantization itself. Now that is not going to be GPTQ quantization, AWQ quantization, or any other specific quantization. It's a normal simpler quantization only, and the format of it is going to be Q4, Q8, okay, Q6. It's a special format, okay, for this particular inferencing engine. I hope the outline is clear. Now coming to couple of next point. So the full form of the GGML is Georgi Gerganov Machine Learning Framework. So it is not GPT generated model language, guys. I have seen at many places, many blog, people are using this particular name, but I think this is not true. Now, guys, here it is a C-based tensor library. As I told you, this library was written in C language. The core GGML library's main job is to efficiently run quantized operation on CPU or Apple Silicon. Okay, so why this GGML library was written? So this GGML library was written so that we can load the LLM. Okay, we can load the LLM, or we can load the quantized LLM. Okay, we can load the LLM or quantized LLM over the CPU, over the Apple Silicon, okay, over the embedded device, okay, over the embedded device,
or over the any smaller configuration. So that was the main or the initial intention behind this GGML library. So ggml.bin format was the old model file format. GGML was using its own quantization format. Now see guys, GGML is not performing the quantization. This was not created to perform the quantization. Again, I am saying GGML cannot perform the quantization. It can load the LLM in one specific quantized format, which is Q4, Q40, Q4K, Q50, Q8K. Okay, whatever LLM you are going to be load, whether it's a normal LLM or quantized LLM. Okay, so it's going to be load in the specific quantized format. The earlier GGML I'm talking about. So the older GGML, it was not tend to perform the quantization. Okay, it was able to load the quantized model but in their own specific format, and these was the specific format. I hope you're getting my point. Now GGUF is what? GGUF is a new standard file format. It's not an engine, okay, which stores model in a single file along with all the metadata. So guys, I would say a GGML is a engine, okay, engine which is executing this gguf file, which is nothing, which is a special bin file with all metadata. That's it guys. I hope everyone is able to get it what I'm trying to explain. Now let's read some more point. GGML itself does not perform quantization. The same thing which I was telling you, right? The GGML ecosystem tools from llama.cpp provide quantization. Means they are converting a model into the bin or GGUF. Mainly they are working with the GGUF only guys, in a quantized format using the script convert.py or convert llama gguf.py. Means what is the meaning of it? Let's try to understand. So guys, as I told you, in initial days, okay, initial days, ggml was there. Now this ggml was the C based library, right? Now guys, this ggml was not able to perform the quantization. Okay, quantization quantization so it was not tends to perform quantization. Okay, was not tends to perform what? Quantization. What? This ggml library. But guys, whenever we are going to be load any hf model, hugging face model, into the ggml, so it was loading on some specific quantized format. Okay, so it was loading in their specific quantized format, this ggml. Okay, so let's say we were having the hf model, any llm. So whenever we are loading it, whether it's a normal llm or it's pre-quantized llm, okay, both we were loading into the specific quantized format. So quantization was not happening explicitly. Okay, one integrated format was being used. Okay, internally it was using that. That's it, nothing else. Now the llama cpp. Okay, now you can see the latest model. That model is called the llama. That inferencing engine is called the llama cpp. Okay, so this llama cpp, actually it is converting model into the quantized model. It is able to convert. Okay, it is able to convert normal model to quantized model. I hope guys you are able to understand almost all the thing now. So let's see. So this was a quantized format, guys. You can read about it. uh, Q4O, Q4K, okay, Q5, Q8. So these all are the format which was being used by the GGML and the llama CPP. So this format is not this GPTQ, AWQ, QAT. So this GGML and the llama CPP is not using this specific format. Okay, which format? The GPTQ and the AWQ and QAT. Now use case wise, so run Llama, Whisper, GPT model on the laptop, mobile devices with the CPU. Originally work with a .bin model file, quantized via GGML format. Model type optimized for the decoder only models, means this generation model. Okay. Now GGML can run standalone, but it mostly used via Llama CPP, which provide text generation, prompt processing, streaming output, partial GPU offloading, and quantized inferencing on CPU and Mac. So guys, llama cpp is nothing, it is an advanced version of the GGML with all this functionality. Now coming to the GGUF. So GGUF is nothing, it's a standardized binary file format for storing and deploying the quantized model. Okay, so we have quantized model. That particular quantized model we can save in a specific binary format, right? It's a physical file. So primarily used in llama cpp ecosystem. Okay, so primarily it was using in a llama cpp ecosystem. It is a successor of the older ggml.bin file format. Okay, naming. So official GPT 5 GPT generated unified format. So this is the official name of it, but community also use this Gerganov journal unified format. Okay, because of this particular person who has created this particular extension. Okay, not extension, this is a specific file. Okay, now guys, design. So it created by the llama cpp community, a self-described format which is containing both bits and the metadata. Metadata includes tokenizer information, vocabulary information, ROPE parameter, okay, special tokenization. Make a deployment easier. Tool don't need manual flag. Okay. Now use case wise, we can load any model, any quantized model into the GGUF. Okay, and we can run it inside the llama CPP or anywhere else. Okay, merely it was designed for the llama CPP. Now let's see the differences. So GBGML is a old one, it's an inferencing engine. Okay, GGUF is a new one. So format type, old quantized format, new unified format. Okay, file extension was the bin file, GGUF file. Tokenizer not including, versioning not including, status still works, means not including. Okay, it was not including any sort of a status. Now tokenizer is being included, version was included, and recommendation to migrate. This means the status and all, everything is being included. Okay, so GGML was the engine which was using this bin file by default, but GGUF is a file format, the unified file format itself, and it is coming up with all these details. Now, what was the problem in the GGML? So guys, separate file for tokenizer and metadata, not version properly, hard to inspect, lack standard tokenizer information, limited support for new tokenization type. Now, on the other hand, GGUF, single file with everything packed, formal versioning, backend compatibility, human readable metadata, tokenizer vocab. So guys, we're talking about the GGML.bin file format. So it was having all these issues. Other than this GGUF is a unified file format which is being used under the llama CPP. Okay, and not only the llama cpp, we can run it anywhere. Okay, after converting uh, our quantized model into the .gguf, or after converting our model into the .gguf format, we can run it anywhere. Okay, but originally it was created by the llama cpp. So guys, this is one line detail. So GGML is scattered file, no proper versioning inspection though. GGUF single standard file format, packed metadata, better quantization support, easy tool. Now if we're talking about the GGML guys, so this is the complete library, complete engine. Here I'm specifically talking about this bin file format which we were using inside this GGML. Now guys, I hope we understood the theory. Now let's deep dive into the practical. Now guys, let's see the practical of the GGML and the GGUF. So here guys, I'm not going to use the classical GGML library. Instead of that, I'm using updated version of the GGML, that is llama.cpp. Okay, so first I'm going to install this CMake and the build essential. So this is the required library. The CMake, basically it is for the C and C++ dependencies. Okay, build essential, again it is for the C and C++ dependency. It is just to like update the compiler and all. So let me execute this both. So my CMake and this build essential is going to be updated. Okay, now after that, see guys, it is running. Okay, it is executing. Why? Because I already executed it before this before starting the recording itself. So let me explain you in that way itself. Okay, I think no need to execute it again, because again it will take a time just to update the CMake. It not here, in the next cell, when it will come, I'll let you know. So just to update the CMake, it takes around basically 10 to 15 minutes. Okay, so let's do one thing guys. Let's understand the code one by one, that what we are doing over here. So first we are going to first guys, we are going to clone the llama.cpp. So here you can see we are going to clone the llama.cpp. Then we are going into this particular directory. Okay, llama.cpp. So here you can see we have a repository. This is my repository. Okay, now after that, what I'll do guys, I am going to be check all the files and all whatever I have inside this particular repository. Okay, then after, I am going to call this make hyphen j. So what it is doing is going to be build the C and C++ related dependency. Okay, hyphen j means it is going to be use all the codes of the CPU. Then guys, I am going to download the model. So this is my model. Okay, which I am going to download it from the Hugging Face. So where you will get this model, you will get this particular model inside the inside this llama.cpp itself. So one directory would be created. The directory name is tiny llama-hf. Okay, so here is my model. Now what will happen guys, so after that you can see we are going to be install one dependency, which is mistral common. If you're getting the issue with this particular dependency, please install it. Then after you are going to be convert. Okay, you're going to be convert your model from this tiny llama-hf to GGUF format. Okay, so once you will run this particular command, so what you are doing, you are going to be use this particular script. Then from this particular folder, you are going to be use the model. Okay, you are going to pick the model. Then that particular model you are going to be convert into the GGUF format. Okay, so this is a specified binary format. If further you want to be convert into the specified quantized format, you can do that also. So here is a command for that. So you just need to run this bin quantize, then this is your GGUF model, and then further you can convert into the Q4. Okay, in Q4 quantized format. This is the native format of the llama cpp itself. We are not going to use any explicit quantization method like GPTQ, AWQ, QAT, right? It is a inbuilt llama cpp quantization format. So this GGUF model, this specific binary model, okay, specific or the special binary model, we can convert into the quantized format. Now after that guys, what we'll do, we are going to run this particular model. So here for running it, I required this main. Okay, then hyphen aim, then here is my model name, and then I will ask my question. Okay, so here is my question, I'll ask my question, and here in how many words basically I want answer, right? So if I will run it guys, if even you will run it, you will not be able to run as of now, because it will give you the error that main is not available. So first of all, you will have to build the main. Okay, so you will check in which directory you are right now. Okay, now if you are into the root directory llama.cpp, you will run this command make directory hyphen p build. Okay, now you will go inside the build. Now under this build guys, you will run this cmake command. Okay, now it will build your all the C++ related dependencies and all, everything it will update over here inside this particular build. Okay, then guys, you need to execute this command hyphen like exclamation make. So once you will execute this command, it's going to be build all the C++ related libraries and all, and this will be your main inferencing engine. Okay, this one, this main file is going to behave is your main inferencing engine, because you will have build over here. Okay, the entire build, the inference build. Okay, now you are going to be check whether you have this file folder or not. Okay, so you can directly run this -ls. And now if you are like sure about this build, okay, see, inside this llama cpp if you are able to get the build, okay, means everything is fine, everything is perfect, you can go inside this particular directory. Okay, now after that what will happen, see, why I'm getting this file and folder, because I'm already into the build. Okay, I'm already into the build, so inside the build I'm getting all this file and folder. So you will have to check whether you have a build or not with a root directory. Okay, you can directly check from here as well. So if you have build, guys, you can good to go to execute this entire application. This is the build, right? So right now I'm into this particular directory, the build only, so I'm getting this file and folder inside it. Then what I'll do, guys, I'll check with this llama cpp. So inside the llama cpp itself I'll be getting either my quantize model or my before quantize this gguf model. So any of them I can use. So as of now I just converted into the gguf model. Okay, I'm going to use that only. So I'm running a command bin llama cli. Okay, then here is what, here is my model name, and then here is my question, and in how many words I want my answer. So guys, once I will execute it, here you can see my cli is updated, my CLI is executed. Okay, and this is the question, what is a quantization, and regarding that here you can see the answer. Now I can ask any sort of a question. So here I'm asking what is Hugging Face. Okay, so let's say if I'm going to be asked what is Hugging Face, is not taking this one. Let me check what is this. Okay, so typically, oh, fine. So it is giving the further answer. Even it might give you the option for writing your own the other questions. Okay, so let me check whether it is still generating or not. Yeah, still it is generating. Now, can you tell me about the training process of the LLM? Right. So this was my previous question. Now it is generating an answer about this as well. So guys, as many as question you can provide. So it will take the question from the CLI itself and it's going to be generate an answer. Now behalf on this one, what I did, guys, I created a rag. Okay, so this is the entire code of the rag. So what I'll do, I will create one specific video on top of it. Otherwise you can go and check out with this particular rag code. Let me give you the glimpse of it, what it is doing. So guys, first it is going to be load the document, that is going to be chunk the document, it's going to be stored inside the vector database, that is files. Now after that it's going to be perform the retrieval process. Okay, now here is my prompt. Now I'm running my code. Okay, I'm running my code, everything, prompt and the given context and all over the CLI. Okay, over the CLI. So guys, this particular thing I'm going to be, see, here is my CLI, here is my model, here is my prompt file and all, and here is my prediction. Okay, then I'm going to be executed with this OI.system. I'll be getting my final answer. Okay, so this is the master code. With this particular function I'm going to be execute everything. So guys, easily we can develop the, easily what we can do, we can develop the RAG system also. Even we can run it inside a local system as well. Okay, that will also be fine. So can you tell me the more about the training process? Once you will hit enter, you will be getting your answer. Okay, or else you can stop the process again, you can execute it, you will be able to get the answer. Okay, so I don't know why it is hanging, maybe because of the memory and all, but yeah, you will be getting an answer, or else again you can start that. So yeah, assistant is saying, see, here is the answer. So I think it is asking about the token. Once you will put the token, maybe then only it's going to be hit the model. Okay, so see guys, here is a user, here is assistant, so everything is working in sync. And likewise, basically you can build a rag on top of it. So yeah, this is it for this particular video, guys. If you like this entire course, then please hit the like button. I'll be coming up with many more courses like this, and I will explain you everything in a very detailed manner. So thank you guys, thank you, bye bye, take care. I'll see you in the next video. Until, thank you, bye bye, take care.